чтобы они открыли. В итоге сегодня вот здесь девушка, которая накрывает по февралю, отдашь эти бутылки? Отдал? Да? Все в порядке? Просто. Не.
Okay, so let's start then. Well, I'm very happy to see all of you here. Welcome to Karelia, to Petrozavodsk. We're going to have 3 days of discussions and talks and networking, and I'm looking forward to a very exciting time and full of ideas and full of, full of all kind of interesting topics which will be touched upon over these days, both in a formal way but also during the coffee breaks and all the activities which we're going to have. I want to say that this is a network meeting, though we try to position it as a conference. There are several networks, and some of the names of these networks you will see here and there, sometimes on the posters outside, sometimes on the slides. So, to make it very clear, we have actually 4 networks or 5 networks which are involved in the whole thing. There are 2 networks which are like really the main ones in this. They are Peril and GDRE, which are the networks which were probably which are the oldest ones and which were initially built like 4 years ago, more or less, right? 3-4 years ago, to start research on fire activity in the boreal zone in a circumboreal scale. Before that, we had these ideas, but we never really had sort of ability to really engage into this activity, to really spread our interest, spread our effort in a more or less efficient way. Now I think this is exactly what's happening. There are 3 other networks. There's a network which is based in Sweden called Nordic Fires, and this network is specifically focused on large fire events. And then there is something called
in Karelian Research Center. And first of all, about this center, we are situated in northwest Russia, and this is very important and one of the largest departments of Russian Academy of Science. And here I mentioned, show you 5 the largest centers of Academy of Science in European part. Komi Republic, some of you were there, Murmansk, Arkhangelsk, Petrozavodsk, and of course St. Petersburg. Karelian Research Center have 5 institutes: Institute of Biology, Water Problem Institute, Geology, and Forest Research. These first four institutes, as you understand, reflect the nature of Karelia. Water, we have 60,000 of lakes and 11,000 of rivers on this small territory. Stones, forest, and biology, biodiversity. And Three Institute of Linguistic Literature and History, it's a typical institute for all national centers. In Komi we have the same, in other republics, national republics of Russia. Institute of Economy and Institute of Mathematics. And the new one, Department of Multidisciplinary Scientific Research, because now it's a new trend, new direction to combine, to complex all studies and of all institutes and have some complex studies. Forest Research Institute was organized in 1957, and now it have 6 laboratories. Laboratory for boreal forest dynamics and production, laboratories for landscape ecology and forest ecosystem protection, and these 2 laboratories works with fires and works with some disturbances in forests, of course with dynamic forests. For forest pedology, for woody plant physiology and cytology, and in your program you can see on Friday some excursion about wood, about some Karelian birch and other some unique trees, unique wood here, and if you are interested, you can visit and you can participate in this excursion. And for forest biotechnology, it's a new laboratory, and of course it's maybe modern and very important for nowadays. And analytical, it's mean that the center of our methods, techniques. This laboratory helps others to work. And here is major research trends: study of structural and functional organization and dynamics of forest ecosystems. These trends are given to us by Russian Academy of Sciences. So this is our task. Scientific foundations of biodiversity conservation, use and reproduction of bioresources, potential of taiga forests, study of ecology and mechanisms of regulation of growth and development of woody plants, and study of the genesis, functioning and biosphere role of forest soils. So this is the main very wide trends of our institute. Altogether we have something like 90 workers and researchers 60, 10 of them Doctor of Science. It's maybe you know that we in Russia have a 2-step degree, scientific degree. It's first the candidates of science. It's something like PhD, or maybe PhD, something between doctor and candidate of science, something like this. And Doctor of Science is the highest step. And here, trends and directions of work, research areas of laboratories. I have said about this some words, and I think it's not necessary to repeat for our main laboratories. Researchers of Forest Research Institute published more than 300 books and a great number of articles. Of course, most of them are in Russian language, so you are not recognize it. But now we try to make some articles in English, and very soon you will know about us much more, I hope. And about international cooperation, few words. Of course, we cooperate with many countries. Here you see our main topics of our cooperation: forestry, ecology, natural resources, management of nature, physiology, soil science, biotechnology. It's our laboratories, maybe the name of our laboratories one more time. And of course, mostly we cooperate with Finland, our neighbor, but not only. We have projects and mutual research with Sweden, Norway, Denmark, and others. You see all this country, and I hope and I'm sure that our cooperation with you and with our neighbors and with our friends will continue and will develop. Thank you. If you have some questions, I will answer. And I hope that we will have possibility to talk about our forests tomorrow during the excursion to Kivac, and we will see what our forests in nature. And so I think we will discuss these problems, dynamic and classification of forests and some other things tomorrow.
Следующий. Где? Это. Вот это? Нет, это. Да. Вот это. Как тебе удобно? А вот он. То есть. Okay. Yeah. Well, now it's my time. I first thought like I'm gonna talk about some conceptual ideas we can apply to make a better networking and sort of develop our cooperation in a larger scale. But then I thought like, it's such a boring topic. Let's talk about science instead. And then maybe in the course of the coffee breaks and all the steering group discussions, we can really go into this and really sort of talk at length on that. So I decided to find a topic which kind of exemplifies the way one can benefit from having access to somewhat larger data set, having access to studies which has been done before you, right, and doing some kind of synthesis of, like in this case, dendrochronological data, but also trying to combine both climate and dendrochronological data in one analysis. This is an example from North America, from Eastern North America, which is kind of far away from us right now, but it still doesn't really falsify the premises which I would like to, the point which I'd like to make with this. That is, the more data you have, the larger the network, the more climate is in your study, the better it is, and at least the more interesting results or more interesting speculations you may come up with. So the study was based in Eastern North America, specifically almost exclusively in Quebec, and it was based on analysis of age structures. We study fire activity, and typically what we do, we look at the fire scars, the structures which are created when the fire comes, spreads in the forest, and then damages the cambium of the tree, right? Trees survive, some of them survive, and then they create something called fire scar, which we can date using tree ring methods, dendrochronological methods, and then establish a date of the fire event. The date of the fire event in this case is pretty exact. It's annual. We'll have annual resolution with that. We can also go to seasonal resolution if we can see the position of the scar within the tree ring, right? So it's quite exact method. And then we can also look for the fire scars in the deadwood, which will give you a possibility to extend your chronology over several hundreds of years. Of course, if you have this deadwood on the site, right? So with this, we can build long-term fire chronologies with a pretty decent, meaning annual resolution. Well, these are the protocol we typically employ working somewhere in Europe or in Eurasia. Why is that? Well, because typically we'll have things left after fires, that fires do not kill trees like in a undiscriminated fashion. There are some trees which actually survive, and we look for these trees and we sample them when they're still alive or when they finally become a deadwood. In many parts of boreal zone, specifically in North America, the fire regime is somewhat different when stand replacing fires dominate, which means that we don't often have access to these finally resolved structures which we can date. What we have in front of us is the age structure of the whole landscape. And quite interestingly, the whole age structure can also be used to say something about past fire activity. Actually, the average age of the landscape is a good representation of the average fire cycle which we have there. And using some rather straightforward or to some degree intricate methods, we can actually reconstruct these fire cycles back in time. In doing so, we actually can build up understanding of the fire activity in the landscapes when we don't have fire scars, right? You always want to have a fire scar, but sometimes you don't, and then age structure will come handy in this situation. So in this case, the whole study is based on analysis of age structures of a landscape. It's not a single site, right? Because you need multiple stands, multiple pieces, patches of forests, but you need a certain amount of them to really come up with a decent estimation of this. Yeah, and this is the study area. You see, it's almost exclusively in Quebec. This is this is St. Lawrence River. This is a part of our big neighbor in the south, and this is the border with Ontario. So I think there's only one part which is outside Quebec. So the scale is pretty large. So you see that each of these squares, which is a single landscape, covers certain thousands of square kilometers. So for each of these landscapes, previous studies managed to reconstruct or come up with the information about the age structure. Of course, you may wonder, well, how we can get the age structure of the whole landscape and sample every single site within this area. Clearly, it's approximation, right? There's certain protocol which people employ to give a representative sample of the age structures in this landscape, right? And clearly, the actual amount of sites sampled is just a tiny fraction in terms of, in comparison to the total area, like shown on this map, like total area of each of these boxes. But still, it's considered to be a legitimate method, so we use that. So the overall idea was to look at each of these areas in a kind of independent way and do two things. First, to look at the current age structure, you always have current age structure, to reconstruct, to get information about the current fire cycle, and then try to see if it has changed over the course of the years, or the course of few last centuries, and then try to see is this change, the pattern of this change, has some meaning, can be interpreted in some meaningful way. So there have been some rather complex methods used, which I'm not going to go into this, but the overall concept of this study was rather simple. Previous research, which has been done largely on the sites, which you all have seen here, has shown that there is decline in fire activity after the Little Ice Age. Right? We'll have this period between 1550 more or less and say early 1800s when it was cold, right? For some reasons, some climatic reasons, of course. And this period has quite particular signature in many processes which we can reconstruct over this period. For example, tree growth. In most places in boreal zone, it was lower than now, just because growing conditions were not nice, right? Trees were somewhat more stressed than it is today. We also know that in places which were well studied, the fire activity was higher than today. So despite the fact that it was colder, the fire activity benefited from the climate settings of that period. So this is relatively well-established fact, at least for some parts of the boreal zone. One of these zones is actually Eastern North America, when we have plenty of research both in paleo and dendron domains. Recently, similar pattern has been shown for Scandinavia. Okay, one thing which though would be interesting to see is the presence of the spatial pattern of this process, the spatial pattern of the transition from period of higher fire activity towards the period of lower fire activity. Why it's interesting? Well, because we see now in the modern data or in the modern climate projections but climate, and specifically fire climate, would likely change. It means that it would be very nice to see how the features of the landscape or just pure climate forcing can drive this change in a spatially explicit way, right? What would be the pattern of this change in actual landscape, in actual regions, right, in the parts of the boreal zone. One question which is actually very interesting to look at is what is the role of vegetation in this dynamic? We have two factors which actually interact with each other. One is vegetation dynamic, because it creates vegetation dynamic, the growth of vegetation creates fuels which are burned during the fire, right? And then we have climate, which actually prepares the fuels, so it will be possible to burn, right? The two things are ultimately needed to sustain fire activity. So the question is, what is the most important part? Is fire is primarily, or changes in fire activity is primarily driven by climate, changes in climate, or it's vegetation which drives the whole thing, right? Why it's so important? Well, can we change vegetation for some management practices? And in this way, we can mitigate climatically driven change in fire activity, right? That would be a reasonable question to ask, and especially something to discuss with forest management, who to a certain degree can modify the vegetation of the current landscapes. Okay, so long story short, we made this analysis, and finally we end up with this picture where you have each site represented by a line, and this line is not straight, as you can hopefully see, right? We'll have certain changes in this certain ups, not so much downs, but mostly ups in this graph. And this line represents fire cycle. Fire cycle is amount of years, time, you need to burn the area which equals the study area. So the larger the fire cycle, the more slow fire activity is, right? The less fire you have. So as you see, the overall pattern is the one which has been shown on multiple occasions in the past, that is, increase in the fire cycle, decline in the fire activity. So you may find it a bit uncomfortable to hear right now, because if you look in the news, like over the last few years, even over the last days, right, the message which you may be getting is that we'll have increase in fire activity across many parts of the world. Recent example will be California. We also had a major fire in Sweden this year. I don't know what happens in France or in some other parts located more south, but in the boreal zone, there is a general belief from lay public, from general public, that there is increase in the fire activity, that there is amount of area burned which is really getting higher and higher. Well, that may be the case, but if you look at the long-term perspective, what you see is that the amount of area burned is still relatively low compared to the historical numbers, compared to the levels we had, say, 200, 300, 400 years back in time. This is just Eastern North America. Actually, more or less similar pattern we see in Scandinavia, and maybe we'll see in some other parts of the boreal zone. Okay. Another thing which you will see from this picture is the presence of certain synchronicity, which is not perfect, but yet we see certain shifts in this fire activity which are kind of happening in parallel in many sites, but there are also some sites which show shifts which are synchronized, right? They occur earlier or later. There's kind of fuzziness in this pattern, right? So the idea was to simply map this and see if we can actually come up with certain meaningful explanation on this pattern. So, and that's exactly what we did. We mapped them, and that's basically the timing of the break in the curve, which is indicative of the largest shift in the fire cycle on each site. Okay? Sometimes we had several shifts, so we just selected the one which was the largest and mapped it. So on both axes you have latitude and longitude, right? Like a map. And then the color would be representative of the timing of the shift. Okay? So this is just the timing when this shift happened. And of course, you may wonder, how can I manage to put them the color across the whole region? Well, it was just a pure, a kriging exercise, right? Which kind of spread the estimate.
And yeah, I do accept that we don't have a really nice coverage of this area. We have some spots where we simply don't have the data. And you may wonder, why is that? Well, because we have some parts of the landscape which are managed and we don't really have the history of natural fire behavior in that part. It's already managed. We have a history of forest use, right? So it's not really the one which we can use to say something about past fire activity. But in some parts it's still there, so we still took a liberty to map it in this way. So what we see that we have a certain pattern there. And if I have oh yeah. So what we see is that the warmer colors, they're indicative of earlier onset of the change towards longer fire cycle. So the onset actually happened much earlier in the western part of the region. It happened, this is more or less the border with Ontario, around here. And then as soon as we progress towards the east, the onset happened at a much later stage. Well, it's kind of interesting. We also said, okay, let's repeat the exercise, but repeat it in a bit different fashion. We knew that in the 1920s, there was a period in North America which was extremely fire prone. And it wasn't specific to a particular part of this region. It's really like subcontinental scale event, where a lot of places were burned to a very considerable degree. We know it from data, from Canadian data, from US data. So we said, okay, let's collect and re-plot the data to represent amount of area which has been regenerated, which was stand replaced, so to say, in this particular period between 1910 1930, and see if we have something there. And that's the pattern, which basically mimics the pattern we saw with this regime shift analysis. Well, what does it tell us? It tells us that there is part of the region which is more prone to changes in fire activity, which is more sensitive in a way. And there's one part of the region which is way more resilient. Right, now you can speculate. Well, let's look at the climatology of the region. We have few features of atmospheric circulation which are very important in understanding the evolution of the fire weather in North America. And these are specifically these two. This is a Canadian ridge and this is a Canadian polar trough. This is West Canadian trough over here. So these are the patterns of level pressure. You can plot it at different heights, so to say. I think often you plot it at 50 millipascal. And they represent sort of quite stable features of atmospheric circulation, which drive weather dynamic during the fire season. So Canadian polar trough, typically it's a region which is dominated by low pressure when you have quite considerable amount of precipitation and amount of days with high fire hazard is very low. So this is the region which doesn't really burn a lot. We see it in terms of just pure weather conditions, but also in terms of the vegetation, where you have a lot of vegetation which is not really adapted to fire in a way that it can resist the fire. It's spruce dominated domain. Though in this part we have around here we have somewhat different situation where climate is somewhat away from the influence of this Canadian polar trough, which results in a somewhat more dynamic situation. The overall resilience of this anti-fire weather, so to say, is somewhat less. So again, back to this. So this is the Canadian polar trough region, which is, as we saw in the pictures I just showed you, has been much less prone to changes, has been way more resilient in the long-term perspective, but also during the specific large fire episodes, which lasted over a couple of decades. So it appears that there are some parts of the boreal zone which are more, and some which are less prone to changes in fire activity. They are more or less resilient. And it appears that there is a climate control of this behavior. I don't have much time to go into the climatic connections, but I can show you that you can make a correlation between fire activity, modern fire activity, and for example, Arctic circulation, and you will find that there's a strong connection between years with increased fire activity and the Arctic circulation. It's this positive relationship. Large Arctic circulation index means larger fire activity, and fire activity which is moved more towards the north, which is simply realization of the fact of strong Arctic circulation index being kind of a hinder for the wetness, for the wet air masses coming up into this region and making fuels slightly less prone, less dry, right? It really keeps this region very dry if Arctic circulation is strong. It's basically has something to do with this jigsaw jet stream behavior. So when it's less, when Arctic circulation is strong, you basically have higher fuel deficits in this, higher water fuel deficits in these areas. And if it's low, then this fire activity moves towards the south. This is the situation when Arctic circulation is high, the value is high, this is when the value is lower. But on absolute scale, it's lower fire activity. You may wonder why it's lower here than here. Well, probably because of the fuels, because as soon as you move south, the fuels become less fire prone, right? We have more deciduous fuels in the south, and they are more difficult to burn, probably because of that. Maybe because of the other reasons, but that's probably one of them. So, coming back to this question, what is the controls? Is it more climate or is it more vegetation? Well, at least with this type of synthesis, that can be debated. We'll have a pattern which happened over the course of just literally a century over here. And you may wonder if it's enough for vegetation to change or to really control something if it happens over the course of a century, right? It's clearly an indication of climate being a more important factor. On the other hand, we'll have this change in absolute amounts of fire activity depending on where it happens. And we also know results of modeling studies that suggest that vegetation do have an impact, right? So again, the answer is probably not definite, but it's something which is very relevant in our discussion, how we can really deliver some meaningful message to the industries, to society, and really come up with certain deliverables which are relevant and can be used to mitigate the dynamic of the fire activity. And probably the last message I would like to say that, again, a lot of discussion that it burns a lot nowadays has to be questioned, has to be taken very critically, because as soon as you go in a longer historical perspective, and I believe even longer perspective, which we know from paleochronological studies, I think Adam will be telling about this quite soon, basically sends us exactly the same message, that we are currently enjoying quite low levels of fire activity, and historically very low levels of activity. So a lot of industries and societies as a whole aligned to these low levels of activity will have to face the challenge of actually aligning to totally different levels, which we should expect, I don't know, in the near future or in a somewhat more distant future, but something which will be coming. And with that, I thank you for your attention and take some questions.
So you say it depends if it's for the forest related, that's driving this cycle, for the climate related. But for the climate projections, it really has a large impact whether it's for the climate-related or the forest-related part. Because the forest-related part is not in the climate projections, whilst the weather-related part might be.
Yeah, that's true. Well, I mean, climate projection has its paramount value in this discussion because it basically tells us the degree of climate forcing we should expect, right? And if you want to come up with a realistic realization of the fire behavior, right, realistic discussion, then you have to evaluate the contribution of fuels, right? And not just contribution of fuels under the assumption that vegetation is stable, but also under the assumption that vegetation will follow the change in fire activity. I think Christel will tell us about that on day 3 of the presentation, because I know it's a major debate in the modeling community how much vegetation actually controls any change and if it follows the fire, because vegetation may exhibit negative or positive feedbacks, right? So you may have more fire-prone vegetation which kind of will regulate fire activity by itself by, for example, reducing the amount of fuels, right? Typically, if it burns too much. I did a study which I didn't manage to finalize by today, but what I did, I tried to look if there's a feedback nowadays, if we look at the amount of fire which burns within the boreal landscape, and this amount of fire has relationship to the following year fire activity. Basically, I was looking for negative feedback, saying you have a large fire this year, and if we can imagine the same amount of climate forcing upon fire activity next year, so we should expect the same amount of fire next year, right? But my expectation and the assumption of negative feedback would be that it will be burning less, because there will be simply not enough fuels, or fuels will be more fragmented in that landscape, right? So I tried to test it across the whole globe, and although results are still preliminary, it seems that there's a modest negative feedback. So there's probably some regulation of fire activity even in today's vegetation. Of course, in the areas when it burns, when natural vegetation dominates, right? We're not talking about Europe or Scandinavia, we're talking about Canada or some Eurasian parts of the boreal zone. Yeah. I don't know if I really moved too much away from the question. Right? Okay, good. So we can take all other questions at the coffee break then. Good. So let's move on and. Yeah, that's right. We have a great pleasure to welcome Tadeusz Splawiński, who is a postdoctoral researcher at the University of Montreal.
No, UQAT.
UQAT. Oh, University of Quebec at Abitibi-Témiscamingue, UQAT, who was brave enough to replace Yves Bergeron today, who unfortunately couldn't come. But we, as I said, will have a really big pleasure of welcoming you, Tadeusz. And Tadeusz will tell us something which may be not exactly the title I wrote here, but I hope Tadeusz will correct it in a second. So Tadeusz, the floor is yours.
Just, you know how to. Okay, thank you everyone. So yeah, as Igor said, my presentation, although similar, is not exactly the same as the one that Yves was supposed to be giving. So I'll be presenting adaptive forest management at the northern limit of commercial forests in Quebec. So just to give you guys a little bit of context, the capacity of forest stands to regenerate naturally following fire is a critical element of boreal forest productivity. And so really we see that it's young and unproductive stands that are the most sensitive to regeneration failure due mostly to limited seed production. And so these stands typically become particularly vulnerable under short fire cycles. And so what we see with the research that's starting to come about is that it's very important to incorporate fire risk and adaptive approaches into both timber supply and forest management planning to ensure sustainability in the long term. So briefly, I'll talk about the most common tree species in the eastern boreal Canadian forest. So the main, really the dominant species in this region is black spruce. So it represents roughly 60% of forest cover in northern Quebec, followed by jack pine, which represents approximately 25%. And then birch and aspen make up most of the remainder with a little bit of fir as well. So I'm going to talk a little bit about these two species' adaptation to fire. So both of these species are serotinous. Jack pine is fully serotinous, meaning it keeps cones on the branches for up to 10 years. Whereas black spruce is semi-serotinous, so typically it has about 3 years to 4 years of cones on branches, but it releases these seeds as time progresses, whereas jack pine really holds on to them for a very long period of time. Both these species produce a very large amount of seeds, and these seeds are wind dispersed as well. In the case of jack pine, it's the thick cone scales and the resin that binds them together that really protect the seeds inside from fire. And so this species typically maintains a very high viability under typical fire conditions. However, even under extreme intensity, it can have a decline in viability. Black spruce does not have the same cone morphology, so black spruce has very thin cone scales. The cones are smaller, they're not as well protected, yet it does remarkably well as well following fire. However, it has typically greater declines in viability than jack pine, but it's still very adapted to fire, and it's able to persist in the landscape under typical fire cycles. And so I'll talk about this maintaining of viability in black spruce a little bit, because it's been quite well understood for a while now why jack pine is so well adapted. So like I said, everyone can see that these thick cone scales really protect the seeds inside, whereas black spruce doesn't have this adaptation. And so if you look in the western boreal forest, white spruce has a similar cone morphology to black spruce, and it typically doesn't do well after fire. And so we asked ourselves, why is it that although the cones are not so well protected, we still have a high viability following fire? And so we came up with the idea that it's the clustering of cones at the top of the tree that actually allow it to maintain viability. So essentially what happens is you have a large amount of cones that form a cluster at the top, and so the cones on the outside of the cluster actually protect the cones on the inside of the cluster from fire. And so we sampled 8 cone clusters in northern Quebec following a fire. We went in approximately 2 weeks after the fire burned. We removed them, and then we sampled cones from various positions along the cluster, and we submitted them to viability testing. And so what we found was actually very interesting. We found that not only does viability increase with height, but it also increases on the windward versus the leeward side. And this is because on the leeward side, you have vortices that form, and so you have heavy mixing of air, which increases the intensity of the fire, and so you end up with a decline in seed viability. And as you can see from the figure on the bottom right, the heaviest losses in viability are typically observed at the base of the cluster on the leeward side, whereas the windward side at the top enjoys the highest rates of viability. So wildfire, as Igor mentioned, is the dominant disturbance in the boreal forest of Quebec, and it's mainly controlled by climate at the continental and subcontinental scale. However, once you get down to a very local or regional resolution, vegetation composition and age structure has a significant effect. And so essentially, both broadleaf vegetation and a young age limit ignition and fire spread. So at a young age, essentially, there's not as much fuel available to allow for ignition and propagation, whereas broadleaf vegetation just has a tendency to burn less. So when we look at northern Quebec, this is a map that was generated of average fire cycles based on a horizon from 1972 to 2009. So we're looking at around 38 years that these averages were calculated. And so what we see is at the top left of the figure, we have the most active fire regime, where the average fire cycle is calculated to be roughly 44 years. And then when you get to the north shore of the St. Lawrence River, so on the right side, the dark blue, there you're looking at 8,000 years. So essentially, it doesn't burn. And speaking about the Canadian boreal forest as a whole, approximately 3% of the fires, which are 200 hectares or larger, are responsible for 97% of the area burned. And so in Canada, it's not atypical to see fire size ranging from 200 hectares all the way up to 500,000 hectares, which is a very, very large area. Now, under climate projections, we see what we're expecting to see is an increase in fire cycle over the next 100 years. However, within the next 30 years, we expect to see negative feedbacks establishing themselves mainly from vegetation. However, the overall trend is that fire activity is projected to increase significantly by the end of the century. And so the figures on the left side really illustrate how within the horizon of 2011 to 2040, you have some of these negative feedbacks producing themselves, but then by the time you reach about 2070 and onwards, you have a continuous increase in fire activity. So when looking at black spruce and jack pine, because these species are well adapted to fire, they typically follow a self-replacement dynamic, which means that under a typical fire cycle, a mean fire cycle of around 100 to 150 years, which is the mean fire cycle observed across the entire boreal forest, when a fire occurs, typically the density that was observed pre-fire is the density that will be observed post-fire. And this is typical not only of black spruce, but also of jack pine. However, it can occur that you'll have a natural regeneration failure. And so what happens is this occurs as a product of two things. Either it's a lack of seeds or a reduced seed viability. And so in the first case, what happens is you have a short interval between two disturbances, or it's a juvenile forest that burns. So in the first case, you can have an insect epidemic, for example, which is followed by fire. In the second case, you have very young forests that burn that are just not reproductively mature, so there's no seeds available to essentially regenerate the stand. Then on the other side, where you have reduced seed viability, this occurs as a product of either very high fire intensity or from prolonged duration of burn. So the intensity doesn't necessarily have to be very high, but the fire is maintained in a certain spot for longer than typically observed, which essentially reduces the viability of the seeds in the aerial seed bank. And so there's a few things that can happen in the event of a regeneration failure. You can either have a decline in density, so the density that occurred before the disturbance essentially declines following the disturbance. So typically if you start off with a stand that's dominated by conifers, by either black spruce or jack pine or a mix of the two, if there's a regeneration failure, this stand can transition to lichen woodland, which essentially is a complete regeneration failure, so the forest becomes non-productive from a commercial standpoint. Or it maintains the same composition, but it reduces in density, so it still is considered to be productive from a forestry perspective, but the density is not the same as existed before. What can also happen, however, is you can have a change in composition. So if the stand that burned had other species present, like aspen, for example, Following the disturbance, that stand can transition from a conifer-dominated stand to a broadleaf-dominated stand. Also, because jack pine typically reaches reproductive maturity earlier and is a little bit more resilient to fire, you can have the stand transitioning from a black spruce stand to a jack pine stand. And when we look at forest management, what we see is fire essentially regulates the age structure of the forest, and the shorter the fire cycle, the younger the forest, as Igor was saying. And so forest management essentially does the exact same thing. Under a typical 100-year rotation period, what happens is you decline the age of the overall forest, and you typically have a decline in old growth stands. So in Quebec, the government had established a scientific committee to examine the northern limit of commercial forest, essentially the limit at which point we're no longer able to harvest. And so they essentially divided the region into three classes. The red is representative of regions where forest management is not sustainable, either because the fire cycle is too short or the stands are non-productive, so there's just not enough wood volume to warrant harvest. The yellow portions are representative of areas where there's significant constraints of fire, but sustainable management is possible if adaptive measures are made. And then in the green portion, we see where really there are no constraints to forest management because the fire cycles are typically long enough that we can continue to harvest without worrying about declining the forest cover. So we conducted a study where we wanted to analyze the risk of regeneration failure in the area, the yellow area that where adaptive measures should be taken, because there is a risk of significant regeneration failure under shorter fire cycles. And so the area, our study area, it occupies an area of 13,000 square kilometers, and this area is characterized by an elevated fire risk. So this is outlined as moderate to high under the northern limit of commercial forest report. And so we developed a model where we essentially use the forest inventory maps within the region. So all the forest polygons have an associated age and a composition. And so we really focused on pure black spruce and pure jack pine stands. We also incorporated the burn rates. So we incorporated the current observed fire cycle from Gauthier et al. From the last 38 years, but we also took the RCP 8.5 scenario of Boulanger et al. 2014, which is the most extreme possibility of fire cycle projection in the future, the most extreme increase. We also incorporated harvest rates. So essentially we varied the harvest rate from 0 to 0.5%, which is what we observe in our study area, 1%, which is the typical harvest rate in the boreal forest of Quebec, and 1.5%, which is more of an extreme management scenario. We incorporated the age of reproductive maturity for both species. So like I mentioned, jack pine reaches reproductive maturity faster than black spruce, but we used 3 ages per species. So for jack pine, we used an age of 10, 30, and 50 years, whereas for black spruce, we use 30, 50, and 70 years as maturity thresholds. The 30 years for jack pine and 50 years for black spruce represent the typical threshold observed in the study area. However, we also wanted to see what would happen, for example, if the trees can reach reproductive maturity faster. So, for example, in plantations on very productive sites, jack pine can actually reach reproductive maturity at a younger age, as well as black spruce. However, on the other end of the spectrum, you can have stands that reach reproductive maturity later, and this could either be from cold growing conditions, which are observed in northern forests, or in productive stands. We used a 25 hectare resolution, and we ran 1,000 simulations per scenario. And so the results from this exercise, under the reference scenario, we simulated a mean fire cycle of 104 years. We employed a harvest rate of 0.51% per year. employing a commercial maturity threshold of 76 years for jack pine and 90 years for black spruce. So essentially for our study area, we calculated at what age on average we should reach a commercial threshold, a volume that's acceptable for forest industry. And in this case, for these results that I'm illustrating, we used a reproductive maturity threshold of 30 years for jack pine, 50 years for black spruce. And so what we see is, for a simulation period of 50 years, we have a median rate of approximately 0.3% of the entire area per year where a natural regeneration failure occurred. However, if we look at the cumulative results for the entire 50 years, it's equivalent to 18.45% of the productive area. So it's quite significant. However, if we look at the results under the RCP 8.5 scenario, they're substantially higher. So here we simulated a mean fire cycle of 57 years on the 2015 to 2040 horizon. And then from 2041 to 2065, 33 years. So this is the projection under the RCP 8.5 scenario. We employed the same harvest rate, the same harvest maturity threshold, the same reproductive maturity threshold. And what we see is that the median rate of regeneration failure per year has now increased to 1.3%, or an equivalent of 65.8% of the productive area over the course of 50 years. So we're talking about a very, very significant area affected by regeneration failure. Now, if we vary the harvest rate, we see that under the current baseline scenario, by varying the harvest rate from 0% to 1.5%, we have approximately a 10% increase in regeneration failure. Whereas if we do the same thing for the future projection, we see that the change increases to 23%. So again, there's quite a significant increase between the two scenarios. Now looking at reproductive maturity, again, we see the same trend. The younger the reproductive maturity threshold, the lower likelihood of regeneration failure. And again, it increases significantly under the projected fire cycles. So now I'm going to discuss adaptive measures that are possible to essentially mitigate some of these effects. And so first I'm going to talk about reforestation. So things like plantations and also the increased production of jack pine and larch. As I mentioned, jack pine reaches reproductive maturity faster, so it's typically more resilient to shorter fire cycles than black spruce. Larch, on the other hand, is not adapted to fire. However, it reaches commercial maturity much more rapidly even than jack pine. You can pretty much harvest a stand of larch after about 40 years on a productive stand. So the idea there is to plant larch mixed with jack pine, and the idea is that in case the stand burns before reaching commercial maturity, a jack pine will be there to regenerate it naturally, but we also ensure that we try having a sustained wood production over time. And so the basic idea here is to increase the growth rate, and this is done through not only the control for spacing, but also using planted stock, which typically grows faster than natural counterparts. We end up with larger stem diameters in plantations, so we maximize wood production by employing this method. However, this requires road access, so we have to maintain an active road network, which can be quite costly. So the treatment of plantations costs roughly $1,000 per hectare, but once we start incorporating maintaining an active road network, this can increase costs significantly. And one of the issues with using plantations, especially under very, very short fire cycles, is that there's a risk of losing your investments due to fire. So essentially, if the stand burns before becoming commercially mature, unless it's large enough to salvage the diameter of the stems, you're losing the money that you had invested at the moment of plantation. And so essentially what this can do is it can use up a significant portion of future silvicultural budgets if these accidents occur over a large area. The other option is to use variable retention, which is more of a passive strategy. So essentially what we do here is we want to assure adequate regeneration in the event of a fire by maintaining a seed source. So rather than just doing a full clear cut and removing all the trees, the idea here is to leave bands of trees that act as a seed source in the event that the stand will burn. The problem, however, is that this has not yet been well developed as a strategy. The exact density of trees that we should leave behind is not well known, and also there's dispersal constraints for the species. So typically for both black spruce and jack pine, you have good regeneration within roughly 1 to 2 tree heights. However, of course, wind starts factoring into it and many other issues. And so this really needs to be tested as an adaptive strategy before it's something that becomes employed at a large scale. What I did was I used a regeneration model that I developed during my master's and my PhD to actually try to determine roughly what amount of basal area you need to leave behind depending on the pre-existing basal area in the stand. And so what we see here is if we want to maintain a 60% stocking within the stand, you need to leave, if you have 15 meters square per hectare of basal area, you need to leave behind roughly 33% of the stand to ensure good regeneration of black spruce, and this declines to 21% for jack pine. However, if you look at a stand that has a very high basal area, this figure declines to 17% for black spruce and 12% for jack pine. And typically 60% stocking is considered an adequate threshold for regeneration from a forest management perspective. If we want to increase the stocking level to 80%, essentially having quite a dense stand with a high possibility of timber production in the future, you're roughly doubling the amount that you have to retain just to increase the stocking by 20%. So it's not necessarily the best idea to try to increase the stocking to 80% because the amount of volume that you're sacrificing at the moment of harvest is substantial. Now, rather than reforestation, another option is to decrease the risk. So what we can do is we could use pre-commercial thinning to essentially do what plantations would do, which is to increase the growth rate, control spacing, and thereby achieving larger stem diameters, attaining reproductive maturity faster. However, again, this requires road access because you have to get the workers on site to be able to conduct these operations. And again, you have this risk of losing investments due to fire. Another possibility is to increase the proportion of broadleaf vegetation because, as I mentioned earlier, it reduces the risk of ignition and fire spread. However, this results in a loss of coniferous cover. So black spruce is really the main species that's targeted by forest industry because the quality of the wood is very high and it has a much higher value on the market. And so it's not necessarily the best idea to switch to broadleaf vegetation because of the decline in value, but also because of biodiversity issues. The woodland caribou in Quebec is currently threatened, and an increase in broadleaf vegetation would not help the situation. It would actually make it worse. So as an adaptive strategy, it's something that can be considered, but it may not be the best option in many regions. And of course, because right now the industry in Quebec is really focused on jack pine and black spruce, it would need to be diversified to essentially increase the production of aspen. Right now, aspen is used for pellets, for wood stoves, for fuel, but other than that, it doesn't have many applications. So the industry would have to adapt and find ways to increase the value of the products and to diversify to essentially make it sustainable. One option, however, is to use the shelter wood system as a management strategy. This is a strategy that's used in Alberta, and essentially you have a double rotation within the same period of time. You end up with a cover of aspen with a subcanopy of black spruce, and the idea is you wait for the aspen to become commercially mature, you harvest them, and then you have the black spruce that take dominance, and then you return about 30 years later and you harvest the black spruce. So you end up with 2 species that you're able to harvest within the same amount of time, thereby increasing wood production and volume. Now, the final adaptive measure is to exclude or reduce harvest. Of course, this is something that forest industry is not very keen on because they would like to maintain a certain level of production. This has important social and economic impacts. If you, of course, reduce the harvest, you're reducing the amount of timber that's available in the sawmills, and therefore there's less employment for people. And so the idea in this case would be to reduce or close certain sectors where the risk of fire is very high and the risk of regeneration failure is very high. In this case, one of the possibilities is to, again, diversify the forest industry to offset losses. So currently, black spruce and jack pine are used for construction, for things like building houses, for making plywood, for pulp and paper. However, this is really just a first stage before it reaches the market. If we're able to increase the value of the actual products that are associated with these species, then we can actually decrease the amount of harvest that we have, but maintain the same amount of money that's being generated. So rather than selling a 2x4, for example, you can sell a chair. And of course, the value that you can sell the chair for is significantly higher than the 2x4. So you can end up harvesting much less, but maintaining the same amount of money coming in. Another possibility, this is really short-term management and something that we have colleagues looking at presently, is pretty much developing an intervention strategy based on observed fire severity. And so the idea is to better plan reforestation efforts in recent burns by identifying fire severity in the canopy and on the forest floor. So as I mentioned, severity of the fire has an influence on the viability of seed and therefore on the amount of trees that regenerate. And so if we're able to make the link between typical fire severities and typical regeneration densities, by using things like LIDAR, we might be able to see which areas of fires we should be concentrating our reforestation efforts in, and which areas of the fire we can essentially leave with no intervention. So this can either be done through on-site monitoring or remotely, like I said, using LIDAR. So essentially the implication for sustainable management of forest ecosystem, what we see is the higher the proportion of younger forests, the greater the risk of regeneration failure. And so future stand volume and productivity is potentially at risk, both under the current fire cycle and under the projected fire cycle. If we want to maintain timber supply, we may have significant increase in the costs associated with it. So things like plantation, salvage logging, road network all become important variables in maintaining productivity. And so what we really see is that we really need to use adaptive forest management practices and strategic planning based on fire risk to reduce the potential for regeneration failure following fire. Thank you.
Thank you, Tadeusz, for a truly exciting presentation. I think we'll have definitely some questions to ask. Okay, I will start. I see that your modeling, you integrate not couple, but quite many inputs, including climate input, regeneration patterns, the severity patterns which you calibrate. If you just take a very broad look at this, what would be the contributor what would be the input which contributes to the highest amount of uncertainty in this modeling? Is it really the climate which makes things somewhat, the projections and the estimates and the measures which you suggest kind of not very definite, not very deterministic? Or is it the biology of the species? So where we can improve the model if we really want to hit the most fuzzy, most obscure part?
Well, the way we developed this model, we took a very simplified approach. And so by using these regeneration thresholds, we use like a binary approach. So if you arrive at the maturity threshold or above, you have good regeneration, whereas if it's below, you have bad regeneration. It's a very simplified approach, but at the landscape level, we feel it's adequate to model the system to have results that we feel are more or less good. We compared our results to those of Girard et al. Of 2009. They observed a 9%, under the current fire cycle, they observed a 9% opening of the forest. We see a 15 to 18% increase, but they only looked at forest opening, whereas under our approach, we're also potentially looking at changes in composition. And so we're not that far off from what's actually been observed over 50 years. I removed the slide because I thought there were time constraints, but we actually did variance partitioning for the model, and we found that the most important factor was fire. Well, the range in fire size and frequency in driving regeneration failure, followed by the age at reproductive maturity, and the final and least important factor was harvest rate. So what we really see is it's a combination of two things. It's the fire cycle and the age of reproductive maturity. There's a lot of uncertainty around the age of reproductive maturity. It's highly dependent on site productivity, for example. And so we're actually presently revising this model. We've actually revised it, and we're in the process of simulating, running new simulations and results. We've actually replaced the reproductive maturity thresholds with growth and yield tables of Potier and Savard. So what we're able to do now is we use a regeneration model to predict the number of seedlings following fire, and then we relate that initial density to the number of mercantile stems over time. And by doing this, we're able to track the basal area, the evolution of basal area of the stand, and hence the seed production. And so rather than just using a fixed threshold, we're actually able to now look at changes in density at a stem by stem level rather than just a binary approach. So I'm very interested in seeing how the results are going to present themselves, because I think this is really the next step in the evolution of the modeling effort. One thing we didn't look at here, I talked about it, but we didn't incorporate fire severity into this model. And this is because it's still something that's not very well understood. We know that there's a direct link between higher fire severity and lower rates of regeneration. However, how fire severity occurs, it's difficult to project because it can either be through prolonged periods of drought or, for example, very high winds, the combination of the two, and you can't really predict that, as well as, for example, modeling just fire cycle by pulling from a distribution of frequency and size.
Cool. Well, I told you this will be very exciting. So yes, and I think we thank Tadeusz for a truly interesting presentation, and I believe it's time for the coffee break. Right? So coffee break will be just outside. Please enjoy.
presentation. Yeah.
Okay. And if I want, what must I do if I want to change my slide? I have to do
This one, no, this one. Yeah, you can use
You can just
this
try.
one. Yeah, and maybe you can use this one. Or this one.
okay. May I just try?
Yeah. Ну, уже, может быть, меньше нельзя, как мы соберемся. Может быть, в 11, может быть, в начале 12. Окей.
But if I want to show something on the
So we can have, yeah, this one. This, just to, yeah.
okay.
This plan.
Okay.
So,
But is it possible to see the next slide sometimes when we put on the diaporama option? You don't know? Okay. 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 We'll have to close to leave. If we want to close to finish it, we want to remove this figure, if we want to remove this ribbon, if we want to put at the end.
so
You know, use arrows.
yeah, just.
To go back forward. So you
Okay.
should use arrow, and to go
Okay.
forward, just left click.
Okay, okay, it's okay. But if I want to leave, to go,
Leave from the station.
yeah, leave the presentation.
Escape.
Escape.
This is the escape. And just press.
Okay. 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 May I?
Continue. So as it is. Okay.
Okay, thank you.
paste. Yeah, the paste command.
If you want, yeah, take this one. Okay.
Okay.
The flash.
Yeah, that one.
And
And then this one.
this one, yeah. Should we
Yeah,
remove it after using?
yeah, I can. And then, yeah.
Okay.
Okay, thanks. This one back. This one.
Okay.
Yeah.
Take care.
Раз, раз. Раз, раз, раз. Раз, 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 раз.
Yeah.
So the lunch, my presentation now it's the one
Okay, but your presentation is
Yeah, my presentation is there.
there. Okay, that's good.
Are you agree with me? I will present after the lunch.
Yeah.
No, Jonathan.
Yeah, that's right. But I just want to make sure because everybody's recommendations.
It's on the computer.
It's on
Okay, my computer's there.
Okay, so we'll use this one.
Yeah. I organize all that with Nino.
Okay, so let's restart. Yeah, so today, now, right, we now plunge into the climatology. You know, we talk so much about climate, but we have so little expertise in actual climatology, quite often. Not all the time, but quite often. So I always thought it of paramount importance to actually secure expertise in this domain for us to really be certain to actually connect to the people doing things with climate. And that's why we have two colleagues of us here, Jonathan, and then we'll be listening to Falmer, who are climatologists, and they will be talking about climate, right? So the first one is Jonathan, and he will tell us about mid-range predictability, which is actually the title of our main network, PREREAL, mid-range predictability of weather patterns connected to fire activity. So, Jonathan, right? I think your presentation. That's right.
Okay. Thank you very much for the opportunity to talk this morning. It's very good to be here and to see some familiar faces from the meeting in Sweden a couple of years ago. So I'm going to be talking about, well, Igor's given the title, but to be more specific, an approach for predicting forest fire activity in the circumboreal region at monthly to seasonal timescales, okay, using an empirical approach. Just to be clear, I now work at Coventry University, which is in the UK, but previously I worked at KNMI in the Netherlands, where I was involved in the development of the pre-real proposal from the beginning. Is there a pointer somewhere? The lights have gone out. I can't see. It's right here. It's right here. Oh, that's it. Okay. Yeah. Sorry. Oh, good. Okay, so within the remit of pre-real, obviously we're focusing on the boreal forests of the Northern Hemisphere. I'm sure many of you are familiar with some of these facts and figures, but this constitutes around a third of the world's forested regions. And the burning that occurs in the boreal forests accounts for around 12% of the total global biomass that's burnt. And this is a main driving factor in ecosystem dynamics. And even small changes in the fire regimes at sub-annual timescales, so anything from monthly to seasonal timescales, can have large impacts on forest composition, regeneration, growth conditions, and consequently on things to do with carbon storage, biodiversity preservation, and impacts on ecosystem services. But particularly at these timescales, the link between fire activity and large-scale climate drivers is not necessarily clear, particularly in this part of the world. In terms of linking fire activity with anomalies in the climate system, some steps have been taken to link fire occurrence with anomalies in sea surface temperatures, for instance. So a recent paper published a couple of years ago showed that around 48% of the global burned area can be forecast using different types of ocean indices, but with rather little success at the high latitudes that we're talking about here. And particularly the relationships between climate and burned area are quite complex and, as we've heard already, dependent to a large extent on local factors. So an alternative is to use climate forecasts that exist already at monthly to seasonal timescales, so forecasts of meteorological variables to tell us something about the conditions that are conducive to fire activity. So in the work that I'm presenting here, we're focusing on monthly drought code, again, which I'm sure many of you are familiar with. This is a monthly version of the drought code index, which allows us to approximate changes in the moisture content of the deep organic layer using maximum temperature and accumulated precipitation or rainfall. And this is used a lot in forest management activities across Canada and northern Eurasia, so reasonably well established. If we look first of all at monthly drought code as an indicator of fire activity, so these, the figure here, the different panels for the different months, are showing the correlation between monthly drought code derived from observations and then average burned area from the global fire emissions data set between 1996 and 2016. Monthly drought code is particularly useful during the summer months between June and August. But the key question here, this is purely produced with observations, nothing to do with forecasts. Can we produce useful monthly drought code forecasts potentially several months in advance, and of what value would that be to forest activity planning? So first of all, just a few words about the prediction system from which we're taking maximum temperature and precipitation forecasts for use in the derivation of the monthly drought code. By far the most useful tool that we have in terms of producing forecasts on monthly to seasonal timescales are dynamical forecast systems. So these are the ones that are based on numerical models that try to represent physical processes. And these are carried out by a number of forecasting centres across the world, but these sorts of systems are inherently computationally complex, computationally expensive to run, and are certainly subject to errors and biases, certainly in this part of the world, that aren't going to necessarily be improved anytime soon. So as part of a previous project, almost sort of a predecessor to this one in terms of where some of the ideas came in terms of from the seasonal forecasting perspective, this was a project funded by EU FP7 called SPECS, and part of this project was about developing an empirical prediction system for seasonal to decadal climate as a credible alternative to dynamical forecast systems. So the system that was developed is quite simple in its statistical construction, but with the benefit of being applicable in a global framework. So monthly forecasts for temperature, precipitation and sea level pressure are produced using this forecast system and then publicly disseminated via the KNMI Climate Explorer website. So as predictors in this system, we're using, first of all, CO2 equivalent, which is representative of the long-term trend associated with global warming, and then a number of indices describing modes of variability in the climate system, in addition to some predictors that vary at local scales. The first iteration of this prediction system is covered in a paper that was published in Geoscientific Model Development. I won't go into massive detail here about the thinking, the philosophy that went into putting this system together, but just to make a few notes clear about how the predictor selection and the model fitting is done. It's based on multiple linear regression, so quite simple in that respect. If we consider that we might have a linear regression model with just one predictor to start with, which is this CO2 equivalent, we can look at the correlation between observations and forecasts for, in this example, December, January, February surface air temperature for the period 1961 to 2014. We then want to look at how many other predictors are going to improve the skill of our forecast. So here we're looking at incremental correlation that's gained by adding additional predictors. So the first one is Nino 3.4, which is an index that represents the El Nino Southern Oscillation. And we can see straight away that in regions around the world with established, well-known ENSO teleconnections, that this predictor is providing a lot of useful information. So in those regions it's included. I should point out that there's a separate model for each grid point in the world, essentially, a separate model fit. So the next predictor might be the Pacific Decadal Oscillation, which once we've removed the signal associated with ENSO, there's not necessarily a lot of the world in which additional information is added here. So we don't want to include it in places where it's not necessarily useful in order to avoid overfitting. The Atlantic multi-decadal oscillation is potentially useful in parts of North America and parts of Africa, and in parts of the far north. So this is something that would be included in those areas. And there's a whole host of other indices that are included here. Before we get on to what we call persistence, which is merely, as a predictor, it's the value of the same variable that you're trying to forecast, but from the predictor period. It's what's known as persistence. So our correlation of if we fit a regression model with all of these useful predictors, the correlation that we get is obviously much better than what we started out with. And we consider this to be, in a global sense, the best that we can do from an empirical standpoint. Okay, so in terms of forecasting the monthly drought code, we've got our maximum temperature forecast that is used to produce an approximation for evapotranspiration. And then the accumulated precipitation is used to approximate a moisture equivalent parameter. And from those we can deduce the average monthly drought code over the course of the month that we're trying to predict. We generate forecasts here under two different modes. I thought it would be interesting to look at two different possibilities here. So historical monthly drought forecasts, or hindcasts as they're known, are generated under these two modes for the period 1961 to 2016. This is in the validation stage. So in mode 1, the forecasts are produced for the entirety of the fire season 1 month before, so produced in March. In mode 2, we again produce 1 month in advance, but we repeat this process throughout the fire season, just to demonstrate what I mean by that. So under mode 1, the forecasts are for each month are generated for the full season. So these are made in March, which is a month in advance, using predictor data from the preceding 3 months. In mode 2, we do the same thing again, but we just do 1 month at a time. So for April, the forecast is again produced 1 month in advance, which is in March, using predictor data from the previous 3 months. But when we forecast May separately, we're producing that forecast in April and using predicted data from, again, the previous 3 months. And this is shifting every time as we go through the fire season. Okay, so we're updating those forecasts as we go along. Okay, so the key questions here are: is there sufficient predictive skill to reliably forecast the full season in advance? And what is the added value of reissuing an updated forecast every month? Okay, so first of all, we want to look at how our forecasts for monthly drought code compare with observed monthly drought code. So under mode 1, certainly for the early part of the fire season, we have a strong correlation with what we would get from observations, but this forecast reliability drops off dramatically in the second half of the fire season. Under mode 2, where we're updating those forecasts every month, we have high correlations that persist throughout the fire season. And more on that in just a second. As a next step, we wanted to compare our monthly drought code forecasts with burned area, again from the GFED4 data set. Because fires are obviously a low frequency event, we're using correlation using spatial means of 7x7 grid boxes here. Again, this is showing the correlation. The patterns for mode 1 reasonably resemble those for observed monthly drought code during the first part of the fire season from April to June. With mode 2, there's not necessarily any additional skill to be gained during the first couple of months, but from July to September, those correlations are consistently much higher. And we can break this down a little bit more to look at the performance at the regional scale. I thought it would be quite interesting to break regions down into homogeneous terrestrial ecosystems rather than to make regional divisions on the basis of political or governmental boundaries. So these are some homogeneous regions in Eurasia. We're just using mode 2 now, having established that this is a much stronger forecast, certainly for the second half of the fire season. And correlations between observations, which are shown in the black line here, and forecasts, which are shown in green, with the spread showing the spread in green showing the spread of the ensemble, and then the dotted line is the ensemble mean that we have there. That correlation is generally between about 0.6 and 0.9 across most of those zones, and then correlation with burned area, which is shown in the red dotted line, not necessarily too clear here, is as high as 0.4 in some regions, which from a seasonal forecasting standpoint is quite strong and significant. For North America, there's less consistency in these homogeneous zones that we see, but there's still evidence that the years of greatest burning can be reasonably well captured. Okay, so as a next step, we wanted to look at individual fires and to what extent individual fires or large fires are associated with a particularly anomalous multi-drought code forecast. So we've looked at the grey dots in these figures are showing occurrences of the largest 10% of fires from this George et al. Data set from 2000 to 2011. What we've done is to match these with the corresponding forecast or hindcast, so the forecast during that month and that particular year that the fire occurred. And we can look at what quartile each forecast falls into. So Q4 is indicating that the value of the monthly drought code forecast is above the historical 75th percentile. And we can see that, in the vast majority of cases here, our forecast is certainly above the median and in most cases above that upper quartile. So what about the very largest fires? And here we're looking at fires that are greater than 500, greater than 1,000, greater than 2,000 hectares. And I'm still thinking about how best to represent this data and to understand the significance of it. But this pattern that we see, that the vast majority of the forecasts that are associated with each of these fires fall into that, fall above that upper quartile. Okay, just a quick summary then. So forecasts of maximum temperature and precipitation have been used to calculate a monthly drought code. This is particularly strongly correlated with observed monthly drought code during the summer months. And then forecasted monthly drought code is able to reproduce the correlation patterns that exist between observations and area burned reasonably well. In terms of how to take this forward, I'd certainly be interested in disseminating these forecasts in the same way that the forecasts for temperature, for rainfall, for sea level pressure are disseminated using the original empirical prediction system. It would also be interesting to do a comparison with between the empirical forecasts and those produced by dynamical systems to understand potentially the value of this approach in comparison to something that's using those computationally intensive computer models. But I'll leave it there. Thank you for listening.
Thank you, Jonathan. I think it was a very exciting presentation. I'm quite certain we'll have questions.
Yeah, I was wondering, so the averaging of the predicted period, so 3 months, versus the averaging of the predicted period. So you take 3 months prior and 7 months after. So these kind of reflect the length scales of the processes you want to capture. So when you go from 7 months to 1 month, wouldn't it be interesting to also shorten your predictor length step to 1 month? Because then I think that you might lose your short time length scale like at indices 60.
So in every case, the forecasts are produced for each month. Yeah. So with that 7 months total, it's a forecast for each month individually, but essentially with different lead times. So the second part of the question is the length of the predictor period. That's something that I decided not to mess around with for this stage, because you could come up with something that could almost be a separate predictor in itself, the length and the lead time. And just for consistency, I've always kept that at 3 months, because that's when we developed the system in the first instance, that's what made the most sense. Should the length of the predictor period be the same as the predicting period? I think it's okay for it not to be, because certainly for the large scale indices it makes sense. Although I take the point that maybe if we're looking at persistence, we're not necessarily comparing like with like. Yeah, so good point.
I'll check.
Yes.
Because it's recording.
I've got a question. Oh no, it's too loud. Okay, I've got a question that is following that, or maybe a comment. The fact that the MDC or the DC, the drought code, has evolution that change over almost 2 months. It's 52 days. I think it's better to take the 3 months at least to include his true behavior on a daily rate, I would say,
okay,
even though you're using the monthly at the end. But I think it's better to take the 3 months for that specific purpose, I would say.
So predict 3 months.
No, no. To take the the previous 3 months as you perform. I think it's better than to reduce maybe to 1 month, because the DC change has a very low speed of change, and it's almost 2 months.
Okay, thank you.
Okay, I have a question. I understood that prediction of MDC and burned areas has been integrating the indices of circulation, right? As you explained, that they were integrated in a stepwise fashion.
Yeah.
Or that. Can you say which indices were driving the behavior of MDC and burning areas in specific parts of the boreal zone? Because that would be quite interest.
Yeah.
Because, okay, for this region we should look specifically at Arctic circulation or Atlantic or like MAO or some others. So you can really see spatial partition of this impact.
So there's no reason why the predictors that are deemed significant or deemed useful can't be extracted for each point and then displayed in some respect. That's something that I haven't done. I know Fulmer did that with the global system, but we haven't looked at it specifically for those variables that contribute to monthly drought code. Obviously, at a given point, there might be indices that are relevant for maximum temperature that aren't relevant for precipitation, and vice versa. So in terms of the predictors that collectively go into that forecast, there could be quite a discrepancy between the two. But forecasting each parameter, each meteorological variable separately, certainly in my mind is a more physically consistent approach. But there's no reason why those plots can't be produced, although maybe not today.
So basically, for the entirety of the grid points which you used in your modeling, you used the same structure of the predictive model, right? You assume that temperature is controlled by this combination of circulation indices.
Yes, but at each point, and for each month, each time step that you're looking to predict, the process of deciding the best set of predictors is independent.
It's independent?
Yes.
Okay, so it's specific to the point.
So one grid point in principle could differ from another. Now that maybe doesn't make sense when you look at neighbouring grid points. It was the best way to approach it in a global framework from the beginning. But when we get down to regional scales, that's at the point where maybe we can be a bit more selective about which predictors make more sense here.
Cool, thank you.
Great.
Okay, so, well, Jonathan, thank you very much indeed.
Thank you.
Okay, we keep on the methodological presentations, climate presentations. So we have Fulmer from KNMI in Netherlands, who will tell us about attribution study, believe it or not. Okay, Fulmer, do you have it?
Yes. Johnson was very good at reading Russian. This one. This one? Or the other one? Yeah, yes. And the mouse is the pointer. What's this one, the pointer? Let's put that there. Okay, so thank you for all being here and that I can be here as well. So this summer I was in holidays in northern Norway, Lofoten actually, and was very much enjoying the nice weather. And then my supervisor emailed me that, hey, when are you coming back? Because whole Sweden is on fire and we need to study it. We need to do an attribution study. So I just continued my holiday. And when I got back, I started on this study. So, attribution of the role of climate change in forest fires in Sweden 2018. I work at KNMI under a pre-project, and I actually, when Jonathan quit it, I took his job. So, thank you for quitting, for going to a different job. So most of you probably already know, but there were quite large forest fires in Sweden in July mainly. I think a total of, I'm missing a zero there, so 250,000 acres, almost, between 200 and 250,000. Interestingly, it was spread out across whole of Sweden almost, and the large part, so this is from the FS dataset. Here you can see the area burned in acres. Here you can see the month and the day. So basically this is 07, this is July, this is spring. This line represents the average, so sort of like a climatology over 2008-2017. And you can see, well, not really a lot, well, that's quite some area burned, but 2018 was much more than normal. So it was quite an extreme event. So let's look a little bit, I'm not sure how familiar you are with these plots, but I think we've already seen the Z500 plot, so geopotential height. And this basically tells us that there was a large blocking event, it's called. So basically the westerly flow was blocked, and then you have this, what the flow does, it goes more like this. So in this part you will have, there's higher pressure and there are higher temperatures, as seen here. So this is the temperature scale, this is in hectopascal, the anomaly. So you see that the pressure was much higher, so the Z500 level was much higher, which basically says the surface pressure is also much higher. So this basically means warm weather, high pressure for a very long time. So it was very persistent and hardly any rain. So what people start asking then is, was this climate change? And what the scientists then ask, how has the risk of the event changed due to climate change? And I want to highlight some words in this sentence. Risk, event, and climate change. And we'll start with event, because what is the event in this case? That's in these attribution studies also maybe the most important step, is how do we define this event? Because often people experience the impact, but if you don't have an impact model, you can't really attribute this, you can't really say anything about it. So we don't have a fire model. I don't think anybody really has in a climate model the actual area burned. So what we do, so we cannot attribute the forest fires itself. What we do, we attribute the forest fire risk based on basically fire weather. And for that we use the Canadian Fire Weather Index. Probably most of you are familiar with it, but it just takes temperature, relative humidity, wind speed and precipitation for local noon and calculates a value, and the higher it is, the more chance you have of forest fires. So it's made for the Canadian region, but it also works quite well for other parts in the world, Mediterranean and Sweden as well. The risk, how do we define the risk? Well, we use extreme value statistics for this to compute the return times of certain events. So once we've defined an event, we can go to observations or climate models, do a extreme value statistics analysis on it, and then that returns return times of such an event. And how do we incorporate climate change? For that we use climate models and observations to get an estimate of basically the pre-industrial climate. Pre-industrial means, well, it means a lot, and people are they're not very clear on when really is the pre-industrial time. Here we took the earliest 20th century because we have climate model data for that. But basically it says when the CO2 forcing is due to humans, is negligible. So basically it was the climate prior to our industrial revolution. And for current and for future climate. So we use, well, it's a bit difficult to get consistent observations, especially for local known data, nicely distributed over Sweden. So instead we use a reanalysis product, it's called ERA Interim, arbitrarily the best reanalysis product there is. So what this does, it gives us a half-degree gridded data set from 79 until 2018, and we use this as sort of the quasi-observations. Of course there are errors in it, but those are not that large. Those are especially with precipitation, they're not that good, but with no precipitation, they're quite good. We use 2 climate models, Easy Earth, well, version 2.3, doesn't really matter, and CESM, large ensembles, both. We chose these data sets and not just something out of CM5 archives, because they have very large ensembles. And if you want to do statistics on extremes, you need large ensembles. If you want to do statistics on 1 and 40-year events, 40 years by definition is, well, then you only have one event. So if you want to find out whether it increases or such likelihood of a 1 in 40-year event increases or decreases, you need large ensembles. So basically, and climate models really help with that, because you have multiple realizations of the same climate for example, 2,000 years. So for Easy Earth, I think we have 500 years or sometimes 1,000. For CSM, it's also in the same order of magnitude. So for example, for current climate, we have a 1,000-year simulation. And for future climate, which in this case is 2 degrees warming, we also have in the order of 1,000 years of data, of daily data, that is. So we decided to look at the fire weather index. So first we need to define the event. So what actually happened? Well, there were lots of forest fires, but how do we define the event in how can we extract that from the observations, from climate models? So what I've done is divide Sweden into 3 parts. Norrland, Svealand and Götaland. Not sure if I pronounced it correctly. And so we've aggregated over those areas, and for those areas now we're plotting. Let's do this with the mouse. Here. So what you can see, the red line is the 2018 value. So the x-axis is just the month. The y-axis is the FYI value, fire weather index, FWI. And the dark lines and the gray lines represent climatology. So this is the median, and the upper one, lower one are the 5 and 95% quantile. And this basically tells us a bit how extreme was this was this event by looking at the fire weather index. And well, logically speaking, you would say, if I would follow the left figure, that you would put Norrland up and then Svealand and then Götaland, but I didn't. Don't know why. So these other ones are a bit mixed up. But you could see that, especially in spring, there were quite high values of fire weather index. And in summer time, and this is valid for all 3 regions, that in July there were also quite high values, but not as high as in spring. Which is maybe a bit interesting, because if we look at this figure, so for area burned, in spring there's not really a lot happening, a bit more than normal. So the main fires are in July. But if you look at the number of fires, so not area burned, but number of fires, then you would see that the number of fires in spring were quite high, much higher, so then it would just go maybe a bit like this. But they weren't that big. I am here. Yes, so I explained this figure. So basically the values were quite high, but interestingly enough, spring values for fire weather index were even higher. So then we check, does fire weather index really say something about actual area burned? Is it a good proxy to use? Because if not, then we can do this analysis, but it won't say anything about actual fires. So what we've done here is a correlation between the observed area burned from 96 until 2012 and the fire weather index from ERA Interim. We've aggregated this a bit to monthly average data, well, for fires, monthly cumulative data, and for north and south. And because there's not that much data, I didn't go the 3 region split up, but just went for north and south. And you can see that, especially in July and August, there's quite a high correlation between fire weather index and area burned. But in spring and autumn, well, with this as an outlier, and I'm not really sure why, but the actual fires, actual area burned in this time of year is very small, so I think we have, well, I'm not really sure. This dotted lines represent the confidence interval by bootstrapping. So it's not just one outlier. So I could have look a bit more in detail, but this is the main thing. July and August are quite a good proxy. July and August fire weather index quite a good proxy for actual area burned. So we chose to define the event as the maximum value of the fire weather index for July and August, so therefore skipping spring, with a 7-day mean, 7-day running mean applied. So basically we do a 7-day averaging, and then we take the maximum value of every year for July and August. And then for every year you get one value, and that's called a block maxima in the statistical extreme value analysis terms. And from that data set, so we have 79, 2018, 40 years almost, so you get 40 values basically for every region. Yeah, so we're not paying attention to spring. It might be interesting to, so this might be related to human influence, that it's actually the people starting the fires, and that kind of decreases the natural correlation between fire weather index and actual area burned. While in summertime, I believe that this is what they found the same results for Finland, and that's what they used to explain these results. So in summertime, when people are on holiday, people-related fires are less. Maybe there are experts in this room who know much more about it than me. But that is what we sort of concluded. So since we've defined the event, we can go to the statistics. So this is an extreme value fit, basically, a GEV. And what this tells us, on the x-axis we have the return times in years. The y-axis the fire weather index. So these dots represent, so this is for Norland only. So this is based on this reanalysis data set. And these dots are basically the observed values, well, quasi-observed. And 2018 is not present here, that is this line. So in a 40-year data set, just to explain this figure a bit, by definition, the most extreme event you can extract is a 1 in 40-year event, because you only have 40 years. After that, the most extreme event you can select is 1 in 20 years. You have 2 of those. And after that, 1 in 13.3 years. So that's basically what you see here. So the most extreme event so far was once in 40 years. After that, once in 20 years. After that, once in 13.3. After that, once in 10 years. So you just rank these values we extracted, taking the maximum July, August values, and then you just rank them and put them once in 40 years, once in 20, once in 13.3, once in 10. And so that explains these dots. And the other line is basically a statistical fit on these data, which allows to extract. So go beyond, so if you have a 40-year sample, to say something about 1 in 50, 1 in 60, 1 in 70-year events, or even longer. But this area, the shaded area with the contours, that gives the confidence interval by bootstrapping. But you can see extrapolating, of course, then the uncertainty goes up quite a lot. So you can see that for Nordland, I've calculated 12.5 fire weather index. It's not that high, but for Nordland it is quite high, and it's also an average of quite a large area. You can see that's basically a 1 in 40 year event. So it matches the most extreme events so far for Nordland. So this, just to explain this figure a bit, and I'll go to all three regions. So we can see, so for Nordland, basically once in 40 year return time. Yeah, that's always, it's not like it will, after 40 years we will have another event like this, but it's just a chance once in 40 years, just a chance of 0.25, 0.025 probability that you can have such an event for in a year. For Götaland it was a bit less, so it was you have quite some values which are higher than the observed event. So it's a once in 20 years event. For Svealand it was a 1 in 15 year event. So they are, well, quite rare, but not unprecedented over this time period. So what we didn't want to see, so it was quite an extreme event, will this change towards the future, or has it already changed relative to our old climate, to the pre-industrial climate? And for that we can do the same with climate models. So it's a bit busy figure, but basically it's the same as the one previous, but now we also plot Easy Earth climate model, that's this red line, for the current climate, and CESM climate model. And you can see they do not completely reflect the quasi-observation, the reanalysis data set, so we have to bias correct them. And we do that, well, there are a lot of ways to bias correct climate data. We do the simple approach, we bias correct for the return times. So basically, for Nordland, the observed, well, it's hidden behind the legenda, very nicely. But the observed value is this line, which gives 13 point something value. So for Easy Earth, it's almost spot on. So for this return time, we select the value representative here. So for Easy Earth, we check whether a value of FYI value of FWI value of 12 point something, how that will change towards the future. And for CSM, a much higher FYI value. So we check if this value will be more or less likely to happen in the, well, relative to the old climate and relative from the old climate to the future climate, which in this case is 2 degrees. So this is how we do the bias correction. It's a relative simple bias correction, I would say. You can do much more advanced, but it's good enough for this. So this is the intermediate step to go to. So this is the same figure as we've shown in the previous slide. So what we can then do, this was the current climate for CESM. So then we can go to only CESM climate model data for the different climate models. So this was the event, the 2018 event, bias corrected. So this line matches this line. And then you can see, so this is present, this was pre-industrial. So in the old days, this was almost a 1 in 80 year event, so quite extreme. Current climate, it's a 1 in 20, 30, somewhere between there event. And in future climate, it will be a once in 7 year event. So this is a bit how this is done. And you can see that for Easy Earth, the fit is a bit different. And basically the impact also a bit smaller, so the changes. And we do this for all the different regions, for the climate models we have. And then we extract it to basically this figure, which summarizes it all. and a bit easier to understand. Maybe not yet, but I'll try to explain. What it shows is the risk ratio. So, and relative to early 20th century climate. So what this tells us, will such an event like July 2018 in Sweden, has this changed? So what's so if it hasn't changed, the risk ratio is 1. Basically the probability of such an event is as large as it used to be. But if it's 2, then the probability of an event has increased by 2. So it's 2 times more likely. If it's 3, it's 3 times more likely. If it's less than 0, it's less likely. So what we show here, first maybe the ERA interim data set. Now from ERA interim data, so this is relative to early 20th century climate, basically sort of pre-industrial. ERA interim doesn't extend that far backwards, it's only until 79. So one could ask, how can we do this relative to pre-industrial control? And then there's a trick in fitting this statistical function, is that it also takes into account the trend. So if there's a decrease, or if there's a negative trend in the fire weather index during 79 and 20, it just extrapolates it backward. And from there you have sort of like your fit for a pre-industrial climate and your normal climate. And then you can say something about the ERA interim relative to pre-industrial climate. So what we see here I've switched it again, all the regions. Maybe I should not do that. So for Götaland, it's actually, so there's a negative trend in observations, quite a strong one actually. So then, this is the value calculated, and this is the uncertainty constructed by bootstrapping. So this is the 1 value. So here it will become less likely, such an event, and here it will become more likely. So there's a large uncertainty because it's only 40 years, so 40 samples, and if you do bootstrapping, then we get a very high uncertainty. But still, the interim says it would be less likely, such an event. And for the climate models, so the red is the present climate and Vegas yellowish is the future climate. And basically we find that for present climate, it's actually not that clear that there's an increased risk of such an event. Actually, some would say, the CSM model primarily indicates there's a less likely chance of such an event. But if we go to, this is especially for Götaland and Svealand, to a lesser extent for Nuland. If we go to future climate, then it's quite clear that such events will become 2 to 3 times more likely. So let's say if it was a 1 in 20 year event, it might become a 1 in 7, 1 in 10 year event. Now I've also done a study. Why is there a decrease in risk ratio? Why is there a decrease in risk for such events? But they're not the figures are not yet presentation quality. Means basically I'm the only one that understands them yet because they're that ugly. But what I could say is that there's kind of this, because the fire weather index is composed of lots of meteorological variables and they do not all have the same trend. So, and it's especially temperature and precipitation that can do different things. And if there's generally a decrease in the risk ratio, it means that there's increase in precipitation. So that's what the preliminary results so far say. It's a bit of a competition between precipitation and temperature. And in the beginning, there's more, the influence of increase in precipitation is more important than the increase in temperature, but towards the future that will change, where temperature becomes more important. So conclusions, 2018 fire weather in Sweden was quite extreme. I'm not saying forest fires, for fire weather, because that's basically the thing we're attributing, which returns are ranging from 15 to 40 years, but they are not unprecedented. Sometimes we find in these studies observed return times of 1 of 10,000 or something by extrapolation, and then they're really, really extreme, but this was quite extreme, but not unprecedented. We find no clear increased risk for such an event for the current climate relative to early 20th century. But for future climate, which means 2 degrees warming, I'm not sure when it is, it depends on us, whether we will ever reach it. We do find an increased risk of 2 to 3 times for future climates, for all regions. So that was it. Any questions?
Thank you, Father. So, questions?
Hello. I think you've covered this anyway. Could you just go back a slide or back to the risk ratios? Okay. So the present climate is the climate of 2018. Yeah. And the future climate is 2 degree warming.
Yeah.
Yeah. Okay. So I mean, this is kind of becoming maybe a newer approach in attribution about, as well as making a statement about the probability ratio or the risk ratio in the present climate. And here we can't say anything that's significant. But by using the same method to extrapolate to 2 degree warming, we can make a statement about that. And I'm just wondering, almost asking your opinion, I guess, when these statements are released to the media and to the public, whether it's sufficient to be able to say we can't make a significant statement about changes in the present climate, but we can be sure that this is a trend that will at some point in the future be significant. Yeah. I guess the question is there a role for a statement about the future climate in an attribution statement?
Yes, I would. Well, that's why we have climate models, to look into the future, and we would like to use them. And this is one application of it. But they need to be treated careful. So, rephrasing of what you said, we can know something for sure about the future, that in the future this will change. Then the sure part has to be removed. So there's because we use these 2 climate models because we need large ensemble data, which is not in CM5 archive. But again, these are only 2 models, and they differ quite a lot. All these climate models, if you look at CMAP archive. So then we rephrase it to our 2 climate models suggest that blah de blah de blah towards the future. So yes, I think use them. But also be very careful how to, and look at the physical mechanism. If it's really plausible, if it matches what we're already seeing, if it matches our understanding, and then you could be quite certain that this will actually happen. But again, be very careful with these, how you phrase it.
I guess the climate trends are quite clear toward the potential effect on fire, but here, even though you do have some simulation with future climate, and in those climate models you do have also vegetation, here, and this is where we have to be cautious when we give the results or explain things, is that we are not taking into account the feedback of the climate on vegetation, which maybe will compensate, and maybe something there will be less things to burn, and actually it will give some echo to the presentation that I will show you after lunch, I guess, where we are trying to dig that. So yes, the trend in the FWI or the MDC is increasing in the future, but vegetation is also reacting to that climate change, I think.
Yeah. So that's basically something I forget to, which is a very big assumption in this figure, is that this is also valid for the future. So this relation between fire weather index and area burned, that this will just hold for the future, which it most likely will not. So in such a paper, the conclusions are, so this take-home message is very short. The list of assumptions is very big. If you want to, it depends how you define your conclusions. If it's based on fire weather, so the fire weather index, then you can just say whatever you want. If you want to go to the next step again and to the actual fires, then there's a whole list of assumptions which needed to be written down.
Of course, but don't worry, I'm exactly at the middle. I'm working on that climate-fire relationship and also on the climate, vegetation and fire relationship, and sometimes it's difficult to...
Yeah.
Question, no one else? Just a quick question, too loud. Is there a possibility to use 20th century reanalysis? Just wondered if you considered that, what the implications were.
Yes, so then you're looking at data constrained by SLP and temperature, I think. And so basically quality of air interim, maybe the variables we're looking at, it's okay, but I'm very cautious for the quality of 20th century analysis, how much you're looking at a model and how much you're looking at observations. So maybe it's better than to extrapolate your trend over 40 years. So in that sense, that would improve it actually, I think. So yeah, we might incorporate it. Interesting question. But you have to be very cautious about these. You really need to know what went in these reanalysis products in order to say something about it. And especially the Arctic, there's hardly any information there. And it appears, or some say, that the Arctic also has quite a big influence on the waviness of the jet stream. Some say not. So if you don't have those included and over the Atlantic as well, it's very difficult to get the correct climatology out of it, or the correct values.
I got a question. So, it's the first time actually following this attribution study, which I found quite entertaining and really enlightening, because you actually can put a number on the event, which in the hands of the general public would be like a unique event, right? You still can discuss the probability of this. But now we work with this composite estimate of fire behavior, right? Fire weather index, which is a product of multiple inputs, like temperature, humidity, precipitation, wind speed, and so on. So I just wonder if there's a possibility to partition these extremes into extremes of these single inputs and say, okay, these change, for example, in the future climate, is driven by like wind speed patterns, right? And not so much of precipitation, or not so much of the temperature. Is there any computational possibility to do so?
So what I did for this analysis is basically to extract when does this maximum value occur for that year, and then select that time step, and then look at the temperature, precipitation. Well, precipitation doesn't say a lot because it's still dry and it will still be dry. So for precipitation, what's happening before. So I've mainly looked at those times when there's the maximum value, and then aggregated those results to see whether between future and previous and future climate there's a change. So that we can do, but if you do the whole analysis for every variable itself, just compute for temperature, take the maximum value, running mean, maximum value for that, then you get all these different events basically. So that's a bit difficult to directly compare, I would say.
Yeah, that's right, because you would need to this integral metric, right, which combines all these at the same time. You need to kind of
so you probably have different events than the events we're selecting purely based on fire weather index. So could be done, but I think most likely you will get maybe the same general outcome.
Okay.
Actually, the same question, but not by splitting the temperature, the precipitation, and so on, all the climatic variables, but the sub-indices of the FWI. This would be a good idea because you would be able to figure out if this extreme event is more related to a huge build-up index with a lot of dry fuel in the humus, let's say, or if it's an extreme event in terms of size because the propagation has been very fast and unmanageable by the firefighters and so on. So you could also target the risk or the event of such events even on the different depth or layer of the fuel. So because the FWI integrates both the spread and the amount that could be consumed, but you could be a little bit more precise, I would say, or accurate on is it more wind and propagation, or is it more like deep fuel? Yeah. I think it would be a very good, except maybe that in a term of statistical test, then you would have to test by combining in a certain way, I don't know, but all the indices test at the same time, it's not doing it each time because then you would increase the error type 1. But yeah, I think it's good.
Yeah, good point. It was on my to-do list, but not very high. But to have a look at it, and but I'll raise it.
Cool. Well, thank you very much indeed, Volmer, for your lovely and thought-provoking presentation. I hope you would agree with me on that. And with that, I think we finish our... Yeah, that's right, we need to think. And I think with that, we finish our morning session. That's right. I see there's already some pressure exercise upon this point, right? So we stop for lunch. I have no idea what's going to happen. Actually, maybe Nina can enlighten us on that. Musky Hotel. It sounds very thought-provoking, but that's probably the place we're going to have lunch anyway, right? And I hope we'll get some guidance how to get there, right? Yes. Yeah, take your money. Nina suggests me to say yes, take your money. Yeah, we meet here in 1 hour, more or less, and a half. 1 hour and a half. Yes. Well, according to the program, right? So, well, again, thank you very much for joining, and see you very soon. Now, see you basically at the lunchtime. Thanks.
Спасибо. Спасибо.
Ouais.
que il y a mais je pense aussi que je peux monter une chose. Oh, oh, oui, comme tu vas prendre, comme ça, je peux les monter. C'est ça, comme tu vas. Ok, parce que le micro est très sensible. Oh, oui, c'est super sensible. Ok. Ok. Ou juste dire le ministère des Forêts. Le ministère des Forêts. C'est plus simple. Oh, ouais. C'est plus simple. I am a forest researcher. Senior forest researcher. Pardon me? I would say senior forest researcher. Okay. Très bien. La présentation va prendre 25 minutes, puis 30 minutes, je pense. Si les gens posent des questions, Yann va m'aider. Parce que Yann est au courant là-dessus de toute la présentation. Donc ça serait intéressant d'essayer de faire une espèce d'échange avec Alain puis les autres. Se mettre en confiance avec Alain et essayer de créer une discussion. Parce que si Alain voit des points un petit peu moins bien compris, lui, il va revenir avec ça dans la discussion. Oui, je me suis tout arrangé avec lui.
Okay. Well, let's. Oh. No, Alexander. Okay, welcome back to the afternoon session. We have a somewhat longer presentation now. I'm more than happy to present Pierre Grandin. Pierre is a senior forest researcher at the Quebec Ministry of the Forest, and over the course of last decade, he has been extremely active, not just researching forest within the frame of his ministerial responsibilities, but also has been extremely active in cooperating and coordinating research done by many of our colleagues, Adam Ali and Christelle, just to mention a few. So this presentation will be done in part in cooperation with people in the audience, because I believe there will be some input from you guys when there will be time for questions and discussion, right? So again, it will be a somewhat longer presentation, but I'm quite certain it will be equally exciting and encouraging. So Pierre, please, the floor is yours.
Thank you, Igor. I'm very pleased to be here. I will present you a synthesis of a research project conducted in the province of Quebec between 2014 and 2017. And this project focusing on the links between long-term vegetation dynamics and also estimated climate change in the goals to improve our ecosystem-based management. The project that I am talking about is a joint project between, as said Igor, my forest ministry, and some paleoecologists, as Adam and others. And the project has been realized with the paleoecologists and some students. I am a kind of representative of all these persons. My role in the project was to help the students in the field and also to comment their proposal, to comment also some publication. And my main goal in all that was to be able to link all the studies together in the goal to present the results to my colleagues at my ministry. The presentation, the main goal of the presentation is to inform you how we describe the natural variability of the territory that I will show you just after, and to make links between the importance of describing this natural variability when we take into account the ecosystem-based management. I am not a paleoecologist. During the last decades, I work on the forest classification of the province of Quebec, mainly the southern part. And this system helps us to characterize the diversity and the repartition of the ecosystems in the province. And this system allows us to characterize whatever we are in the province. If we know the species composition, we are able to go at the other levels of the classification system, and at the end of the system we are able to characterize the local vegetation to a circumboreal distribution as Canada and Russia. But after having produced this system of classification, we want to understand their long-term evolution. It's why we studied mainly here the western black spruce moss subdomain. Our project has been specifically done there, and in this presentation I will explain you how we define the natural variability of this territory, the links between climate, fire regime, and the evolution of the vegetation. All this project about the natural variability is based on the concept of ecosystem management. The ecosystem management is based on the description of the natural landscape, which correspond to a landscape not or slightly affected by human activities. And we compare this landscape with the current landscape, which has been mainly affected by logging. And by comparing these two states, we can identify some issues, and these issues are taken account in the forest management plans. But now, when we define the natural landscape, we use only the contemporary dendrometric data, which characterize only the 200 last years. Now, the concept of ecosystem-based management is an evolution to take into account also the change in the future climate, and also to give more importance to the long-term natural variability. The goal of our project was really to characterize this long-term variability of the black spruce western subdomain. Finally, we know that the goal of the ecosystem management is to compare the past with the future in order to maintain the main attributes of the ecosystem within their range of natural variability. proceeding like that is the best guarantee for ensuring the resilience of the forest. We see this sentence in many papers, but I think it's a central sentence about the main goal of the ecosystem-based management. Our ecosystem-based management is also based on a reference condition register. Is a report where for each of the subdomain of the province of Quebec, we describe the landscape age structure and also the forestry composition. For example, in our subdomain, the fire cycle is close to 150 years, and when we apply the Van Wagner equation about this fire cycle, we obtain this landscape age structure, and the analysis of this structure inform us that the percentage of old growth forest is close to 50%. Some of these forests are protected, and some others are exploited with partial cuts. The importance of old growth forests is a very important element in the forest management plans. To describe the natural variability, the first element that we consider very important is to have a good understanding of the contemporary vegetation. In our study area, we have a lot of information about the vegetation and also the physical feature as the superficial deposit, drainage, slope. And we use all this information to make some numerical analysis and produce this map. And the numerical analysis inform us that the proportion of jack pine in the different regions was a very important variable. It's why we characterize the 4 regions that we see here in relation with their abundance of jack pine. In the purple region, the jack pine is very abundant. In the blue and green one, the jack pine is in moderate abundance. And in the red region, the jack pine is relatively rare. To describe also the natural variability, we must have a good understanding of the importance of human activities on the territory. This map shows us the importance of this activity. Each color indicates a certain period and the forest activities that has been done. For example, in this area, the forest management, the forest activities has been done only mainly between 1910 and 1950, and the forest activity increased with the time, and in this region, one landscape is considered to be outside of the natural variability, because there we realize since a very long time many forest activities, many fires are natural and others are anthropogenic, and we consider that it's very difficult to manage this forest in order to recreate the natural or to be close to the natural landscape. The goal of my presentation is describe or to inform you how we have produced the natural variability. Here we have just an example of the result concerning the climate. I will explain you how we have obtained this result, but the natural variability is described by this kind of information, and we will put also some information about the fire regime and the vegetation. And by working on this characterization of the natural variability, 4 questions are very interesting for us. The first question was, did temperate species have already been present in the region during the Holocene? This question is important because if the temperate species have been present in the past, they have the possibility to also to be present in the future with the increasing temperature. The second question, do all the regions of the study area have the same contemporary and Holocene forest dynamic? We consider this question important because if each region have a specific contemporary and Holocene evolution, we want to be sure that we consider this difference in the ecosystem management. Third question, are the proportion of the old growth forest presented in the reference condition register? This reference register have been built only considering the dendrochronological data since the last 2000 years, but is this reference condition are representative of the long-term variability? It's an important question for our forester. And finally, will future vegetation resemble that of the warm periods of the Holocene? To describe the natural variability of our region, we use 3 ecosystems because 3 of them give us complementary information. The first ecosystem are the lakes, and in the lakes we work on charcoals, pollen, and also chironomids head capture to reconstruct with the chironomids the paleo temperature. Some studies have also been done on the peatlands, and in the peatlands we studied charcoals, pollen, macro remains, and also testate amoebae. Testate amoebae allow us to understand the variability of the water table in the peatlands, and to associate that with the variability of the precipitation. We have also information about the forest, where we take some charcoals at the junction between the humus and the mineral soil layer to date these charcoal and describe the fire regime. And also, in our goal to describe the variability, we sample a lake with more precision than the others. Around this lake, named Lily Lake, we sample the lake, we core the lake, we sample also the peatland and the forest stand, in the goal to compare these 3 ecosystems and to understand their complementarity. Because at the beginning of our project, we have the choice to study in some ecosystem, but one of our preoccupations was to understand how these ecosystems can help us to describe the natural variability. And our investigation, unlike Lily, help us to understand this knowledge to all our study area. For example, knowing many things about Lake Lily, we were more able to work or to understand the natural variability on the lakes and the peatlands located in the same region that Lake Lily, which correspond to the green color. Now I begin really the description of the natural variability. First, we are interested to understand the variability of the vegetation. We are here a pollen diagram of Lake Lily, and we can see different period with a specific forest vegetation. At the beginning, 8,000 years ago, during 1,000 years, jack pine was abundant. After that, temperate species until 3,000 years were well represented. It was not a temperate forest, but boreal forest species, but it was a boreal forest with temperate species. And after that, since 3,000 years, the boreal species are more abundant, and since 1,000 years, jack pine is slightly more abundant. Here it's the illustration of the changes in the vegetation. And this information helps us to answer our first question: did temperate species have already present in the region? This diagram is the demonstration that the answer is yes. Now, knowing information about Lake Lily, as I said previously, we extended this information to have a better information about the green region. More specifically, we take the lake information and we describe it for each millennium. And this description of some lakes about each millennium have been submitted to some numerical ecology to produce an ordination. The first part of the ordination show us the affinities between the species. For example, jack pine and Alnus crispa have affinities. They are present together in some millennia. It's the same with black spruce and balsam fir and the temperate species. The other element of the ordination give position on the ordination each millennium. And by comparing the position of the species with the position of the millennium, we can follow the evolution of the vegetation from each millennium to another. From an example, the red dot here indicated the abundance, the increase of abundance of jack pine during the last millennium, and the blue dot indicate that at the beginning of the Eocene, there is 7,000 years here, also jack pine was abundant. This information allows us to also answer to our first question and also to our second question, because this evolution of the different millennium have been done for the lakes in each region, and it clearly appears that in the purple region that Thaddeus told us at the beginning of this conference, that all the millennium has concentrated in the jack pine area. This information demonstrates that in this region, the purple one, at the beginning of the Eocene, the landscape were already dominated by the jack pine, and it's still the same in the contemporary landscape. In the blue and the green region, it's the same than Lake Lily. It's this evolution, an increase of the jack pine during the last millennium, and a good representation of jack pine as the beginning. And when we look at the ordination of the millennium in the region dominated by the peatlands, all the millennium are located in this section of the ordination. Finally, all this ecological numerical treatment analysis demonstrate that each of the regions have a specific evolution, and this evolution began right after deglaciation, of the drainage of proglacial lakes. If now we are presenting the natural variability about fires, at the beginning I talk about the local variability. For that we talk about the information we have on the fire regime of Lake Lily. I said just before that we sampled the lake, the peatland around the Lake Lily, and also the mineral soil. And what is the answer to these three ecosystems concerning the fire regime? We see the evolution of the vegetation that I presented before, and here we can see that the fire has revealed that in the lakes are constant, are along the Holocene period, but something is missing here during the last millennia, and the forest charcoals and also peatland charcoal give us a better information for during this last millennium. It's the first time that in the world a lake is studied by comparing lake, peatland, and the mineral soil, and this information has been. With this information, we produce an article with Adam and many other people. Now, what is the fire regime at a regional scale corresponding to our green region, where the jack pine is moderately abundant? We studied the mean fire interval, which is the time between two subsequent fires, and with this information we were able to reconstruct the variability of this variable, the mean fire interval, which has relatively short during the jack pine period. After that, the mean interval increased, fire were less frequent, and after that, since the increase of boreal forest corresponding to the borealization or coniferous, what is the word? Coniferous.
The increase of coniferous species.
Okay. Coniferous. Okay, and we can compare the mean fire interval with what is proposed in the reference condition. We see that the reference condition is representative of the last centuries, but not the older centuries. And with this information, with this important information about the fire cycle, we were able, with our student, our PhD student, who was treated these data to transform the fire cycle in a proportion of old growth forest. We see here the proportion proposed by the reference condition, which have been, I repeated, about only the last 200 data. We are able to extend this understanding to all the Holocene, to see that the Holocene variability of the old growth was varying between 35 and 70%. The actual reference conditions are good, but it's the first time that we can expand this information to all the Holocene and to define a variability. It's here a main result of our project, because we can give more information about the reference condition we used in our country. Here we have a synthesis presentation of the natural variability, I didn't talk about the climate variability. We see here the results given by the chironomids, and mainly we can see that at the beginning of the Holocene the temperature was higher than today, and we see that the chironomids give us a very fine variability of the variability of the temperature. And also, I don't know if you see, but we can see that in gray color that some periods where the climate was warmer or colder than today. This variability is important because it helps us to understand that since 3,000 years there is a decrease of the temperature, but also an increase in variability. And more we understand that these two elements, colder climate and variability, climate variability, is one of the main elements which explain the transformation between a landscape dominated by boreal species with some temperate species to a landscape really dominated by boreal species. This description of this natural variability is very important for our ministry, and we would like to have some information to all the subdomains in our country. When we compare these elements, mainly the temperature with the temperature expected in the future under different scenarios, we see the more probable scenario, these two ones, we see that the temperature will be, the future temperature will be higher than the temperature we known during a long period of the Holocene. And when we take the worst scenario, the temperature will be higher than all we have known during the Holocene. As our last question, will future vegetation resemble to the warm periods of the Holocene? The answer is what I just said. Finally, in conclusion, temperature and the conclusion are linked to each our main question. Temperate species have the potential to migrate in boreal forests because the future climate will be favorable. But it's important to understand that jack pine and fire have increased during the last millennium, and in the future we expect also an increase of fire. Finally, the migration of the temperate species will have probably a major. The fire will probably be the most important adversary to the migration. Probably we will see a fight between the temperate species which can migrate in northern region and the fire will stop this migration. The proportion, third question, the proportion of old forests has varied significantly all along the Holocene. Considering that, we propose favoring a strategy of partial cuts. We have already a good strategy, but our result reinforce the importance of this silvicultural treatment in a context of climate change. Question 2. Each region has its own specific dynamic. Specific strategies as and planting jack pine, as Thaddeus told us talking us, and conducting monitoring survey must be initiated in this region with high fire frequency.
This proposal is currently implemented in the province. Finally, we limited our commentaries on the peatland in this presentation, but this ecosystem is well represented in our study, and this ecosystem is exploited by the forest company. Our result that I don't or only shortly presented here also confirm that we must monitorize this ecosystem. Dense plantation of larch are actually under study to limit the increase of water level after log and also after fire will be supposed to be increased in the future. This ecosystem will also be characterized in the future by an increase of carbon emission. It's why study the wetlands is very important. In conclusion, about the links between the knowledge of paleoecology and the ecosystem management, it's sure that paleoecology doesn't give us a specific treatment as ADS present us, but we consider that we consider that to have a better understanding of the evolution of our ecosystem help us to have a better forest management. Knowing all these elements, probably I take your example, Thaddeus, considering that you have a better understanding of the past evolution of the ecosystem you studied, probably you will be a bit influenced by this knowledge in your thinking about the determination of the best treatments in, for example, the region where the fires are important. Okay, thank you. It's finished for my presentation. And if you have some questions, Adam will help us to give an answer. The most important is to have you understand how we have described the natural variability of our region and how this knowledge can be used in forest ecosystem-based management. Do you have some question about that? And I hope I was enough clearer. Okay.
Thank you, Pierre, for very profound overview of long research projects, and probably that would be like what, 5-10 years, last 5-10 years this has been running, right? So I'm quite certain there will be plenty of questions people will be asking, and I see only one on the back, right?
No.
There are no permafrost, just many peat in this region.
Yeah. The red region is dominated by peatlands. Yeah, and in this region we realize two important studies, and each of these studies conducted to a publication. In the first study, we elaborate a transect from the Lake Lily to the forest. It was a 1 kilometer transect, and at the base of the peat to the contact of clay soil, we sample the last 50 centimeters of organic material. We have, I think, 15 samples of 50 centimeters, and for each of them we study the macro remains and also the fires. And this study helps us to understand the effect of the fires on the vegetation. After the fires, we saw a general increase of the water level. And it's important to understand this element, because in the future, probably the fire will be more important in the peatlands, and this fire certainly will affect the water level of the water. It's why some projects on silvicultural are to be planted with a high density de larch to try to avoid the increase of the water level. And the second study was about one profile along our transect and along this core of 1 meters of peat. A guy in the province of Quebec, Gabriel Magnan, studied the evolution of the macro remains and also the state amoebae in the goal to reproduce the water level all during the Holocene and make with this information some relation with the variability of the precipitation. It was for our country the first so complete paleoecological study, because many people study the vegetation, but only the contemporary vegetation. They go in some place where the last fire happened in the 1910, they go in another place where the last fire happened in the 1820, and another place in 1750, and with this different information, they try to reconstruct a kind of trajectory of the evolution of the vegetation, but this information is partial for us. Now we have a real idea of the evolution of the peatland vegetation with these two studies.
Yes, if I cut your point right, your basic idea is that defining the proportion of old growth forest, you can find it from fire cycle.
Yeah.
So when the fire return interval is low, the forest may have been old. Now I'm asking you whether you consider that may have been other disturbances in the past, apart from fires, like for example storms, plant disease outbreaks, extreme weather events like really cold winters, which also can regenerate the forest, even when there is no fire.
Do you want to give an answer, Ade?
Yeah, I think that the main disturbances in Canada have two kinds of disturbances. Mainly insect outbreak. That's the main host is. I think that I can talk.
Sorry. Okay. We have two kind of main disturbances. Insect outbreak with the main host species is a fear, is Abies balsamea, and also the second host species is Picia mariana. But we have a colleague that also use macro remain and head capsule of this species to reconstruct this past dynamic of this outbreak. But it's very partial because it's not easy to have these informations. So now it's quite sure that we only use charcoal as the main source of information about disturbances. But I think that in the past we have also this type of disturbances that could also impact the vegetation and also the proportion of old forests in these ecosystems. But we can I think that we can say that fire is the main disturbances that control the vegetation's dynamics and composition over times. But we cannot exclude that other disturbances also had played a key role in the past. But
I think probably our main problem in our study area is we miss lakes. In the green region, we had only 3 lakes, and other regions we have close to 3 lakes. But at the beginning of this study, Adam began this study maybe 10 years ago, and the idea was just to have some information in the peatlands region, and after that to go in another region where the fire regime was totally different in the purple region. But now, with time, we realize that maybe the first element before begin paleoecological studies, we must have a very good understanding of our contemporary diversity of the vegetation, and after that, to use this information to sample in the best places, in the goal to be able to compare and demonstrate that each of them has a specific evolution. Are you agree with that, Eden? With the time, the ideas, there is an evolution in our ideas, and now the preoccupation to try to distinguish that the natural variability is distinct between each region was not there at the beginning.
I think that we have a main frame that I think that I will present some data. I think that Friday about it. But the main information that we have, because now we have a lot of sites between the east and the west part of the boreal forest of Quebec, and obviously now we are able to say that the beginning of the Holocene is more active in fire, and the end of the Holocene, and I think since 3,000 years ago, we have a decrease of fire activity related to a decrease of insolation and increase also of precipitations that induce a decrease of fire activity. But we have some part of our study area with high variability, because the vegetation is the same, you have not the same type of soils, and this kind of heterogeneity induce also some variability in fire activities. And you have some part, notably in the clay belt, when we can record an increase of fire activity during the late of the Holocenes. So this type of heterogeneity need to be documented, and but we don't have now the main response about how we can document this variability. But the main point is that this difference between the clay belt and the other part of the Quebec regions is the impact of the clay belt and the soils, and the development of peatland in this area, because you have a large peatland. And I think that this the development of this peatland during the neoglacial period, when we have an increase of precipitations, induce this kind of variability in the fire activity. So the show must go on.
And in the future, with Adam and others paleoecologists, our goal here it's a region with sugar maple, and under the future climate, the maple sugar have also the possibility to migrate in the boreal region, and we would like to understand the potential of this migration by using paleoecology.
Excellent. We have more people interested to challenge these findings. Okay, cool. So I think with that we thank you. We thank Pierre again for very instructive overview of what has been going on in Quebec, and hope that it will be even more instructive in the years to come, right? When the project will finally be finalized, which is not really finalized at this point of time, right? It's still ongoing. The project.
Excuse me, I don't understand what you say.
I'm just wondering, is it still ongoing project?
Yes, it's still ongoing project, but the main point is we have a lot of lake, but we need to have some funding to analyze them.
Yeah, because that wants to hold everyone here, so that's
is the big issue. But yes, we have some project also here in Eurasia. So now we need to deal also with Quebec and in Canada, and also our project here in Siberia and in the Republic of Komi. So we have a long period of time to do all things, I hope.
So we need students and funding.
Yeah, we need students, and to summary, we need students and funding. Yeah.
Okay, cool. Well, thank you very much again. And now we need to decide. I really give it up to you guys. There's a possibility to go for another break, or we can continue straight to the next presentation. It's up to you if you feel. Well, I hear the voice about the breaks being very important. So let's change a bit the schedule, have a break, and then continue as it is. Okay? So break time.
Since everybody's back now from the coffee, I'm just holding up for Igor for a little bit. We will continue now with the presentation from Professor Viktor Voronin. He's the head of the Department of Experimental Botany in Irkutsk. And afterwards, he will also have a poster there, but the questions about the poster will be answered at the poster time. The stage is yours, Professor.
Thank you. Dear colleagues, let me present this report. The purpose of our work was the creation of a long-term chronology of large-scale forest fires on territories of the Baikal region, revealing their repeatability for forecasting occurrence of fire hazard as well. The large-scale fires are understood as an occurrence of the centers simultaneously in two and more of the investigated areas. Our research was conducted in the following administrative territories: Irkutsk, Bratsk, Olkhon, areas of the Irkutsk region, and also in Barguzin and Alla, Kurumkan areas of the Buryatia Republic. The basic object of our study was Pinus sylvestris. In order to perform the dendrochronological analysis and forest fire dating, we collected tree samples from 6 pine sites in subtaiga pine forests of southern areas of this territory. We cross-dated 153 fire-scarred trees and recorded total 56 fire years from 1589 to the present time. The pine has this slide demonstrates pine forest in the site Barguzin. You can see fire scars on the trees. This is pine forest in the site Harga and pine forest in the site Olkhon. This is pine forest in the site Bratsk. Pine has a long-term increment depression a year after a fire and within several years after it. For example, the fire in 1978 and this you can see a depression of increment. Testing for the occurrence of a large fire was obtained on the basis of the analysis of radial increment depression in not less than 25% of trees. We selected the course and stem discs of trees in a forest stand on the area not less than 3-5 hectares. As a rule, we sampled more than 20-30 trees in each stand. Fire events were reconstructed by using proxy fire scars in records from cross-dated training chronologies. Individual training chronologies was constructed on the selected increment course. For the further construction of the averaged chronology, the individual chronology having more number of synchronous reflexes of the periods of the increment reduction caused by fires was selected. Dated individual pine chronologies were subjected to the procedure of standardization and united in the averaged chronologies. Calculation and the analysis of the response function under the basis of climate factors were carried out in the software package DPL-99. The analysis of time and frequency structure of the received chronologies was made with the Fourier method of direct transformation. Intervals between fire years were calculated as the relation of the duration of the received time lines obtained for the habitat of each tree stand to the number of fires fixed for this period. Dates of the fires allocated on the fire scales with comparison to changing offerings in Allah chronology are shown on this slide. It is well visible that fires cause a clear decrease in the radial increment, a negative deviation of more than 1 sigma, within several years after a fire. Strong draws can also cause a very strong reduction of a tree ring height. For example, the draws of 203 caused a very sharp reduction of a tree ring, a negative deviation of more than 2 sigma. However, already in the following 204, the tree ring produced with which was above the average level. In a case with fire damage, the depression of an increment has long character, and the ascent of the ring height on an average level occurs during a number of years. Thus, it is possible to confidently separate the fire hazard on the consequence of drought years. Taking the above considerations into account, we could identify fire depressions of a radial increment of a pine in this chronology. As a result, dates of 58 fires were determined. In a similar way, dates of fires in all the investigated areas were reconstructed. The creation of generalized tree chronologies of different research areas is carried out by the purposeful selection of an initial material. The individual chronologies having both a close correlation and a larger number of synchronous periods of radial increment during a fire was chosen. Generalized chronologies were saturated with information materials about the fire history of the given area. Comparing the graphs of chronologies from 3 different areas, it is possible to notice that until the beginning of the 20th century, fire depressions of the radial increment periodically occurred at different times. But in the last century, the happened a synchronization of fires in all areas. In this time, significant increased population in the region. Received chronologies were verified by other information sources. We used fire chronologies received on dating fire scars and on analyzing terrain chronologies for pine and large stands in the different taiga zones of Siberia, pine forest of Mongolia, and pine forest of the Komi Republic by Igor Durobyshev et al. Last chronology. Comparative analysis of all the fire chronologies showed the following dates synchronous with our dates in time. A comparison of the obtained chronology with historical date of Siberia and Mongolia over the past 500 years has become a new, for us, new approach to date verification. In this slide is a fragment of this chronology, historical chronology. A lot of the dates relating to fires that occurred in the more than 2 areas examined by us find a direct or indirect evidence in the historical information. Dates over the past decades were already checked according to the official date of administrative bodies and some scientific publication. As a result, after the date verification of the fire chronology in the Baikal region using various information sources, more than 78% of the dates of forest fires were confirmed. Such a high accuracy of their allocation allows us to draw a conclusion on the reliability of the chronology of forest fires received over the last 4 centuries. There were detected the following periods, which were characterized by the increased fire hazard, as well as certain years when fires were recorded in most chronologies. On the basis of these investigations, we found 16 periods of important fire activity from 1609 to 203. The mean time between the fires varies from 9 to 22 years, depending on forest type and human activity. Whereas in the 8th century, the mean time interval between 2 fires was 19 years. It is only 11 years in the 20th century. The peak of spring fire hazard in forests of the Baikal region comes mostly in May, on a backdrop of insignificant amount of precipitation and low relative humidity of air, no more than 30%. Small precipitations in June keep fire hazard from this month. We determined the relationship on the received chronologies with air temperature and precipitations on the fire hazard period. For the analysis, significant correlation factors for the radial increment with the May-June precipitation were obtained. This slide shows a chronology of the summary schedule of all the surveyed areas over the past 100 years on a backdrop of a change in the selected dominant climatic factor of the total amount of precipitation in May-June. The dynamic of precipitation of this period clearly describes the dynamics of positive and negative values of the radial increment. Fourier transform, where the dependent components were actual values of the generalized chronology and independent the amount of May-June precipitation, showed a set of cycles which determine the periodicity of occurrence of forest fires in the region. Among century 60 years cycles and among intra-century 3-4 years cycles. These cycles show the tendency of the chronology of the fire dates, determined both with the fire scales and with the Fourier tree-ring chronologies and the wavelet transform of tree-ring chronologies. The revealed cyclicity in tree-ring chronologies and the relationship of this process with spring-summer humidifying give the basis for construction a forecast of fire hazard occurrence in the medium term. Our research was carried out in 207. According to the cycle decrease of summer precipitation, we should expect the highest fire activity since 213 to 216, when the minimum of summer precipitation was reached. The given slide provides information of forest fires over the past years. It is clearly seen that our forecasts provide to be true. This is data of number of forests on the burned area. And conclusion. We reconstructed the history of forest fires for 6 tons of mixed pine woods in the Baikal region. It was found traces of 56 forest fires which occurred in the past 4 centuries. Besides the scars on the trees, we also used the reduced growth of the trees after a forest fire. From 64 fire-scarred samples and 6 tree chronologies, we could deduce 40 forest fires within the last 3 centuries, which occurred simultaneously at 2 or more of the investigated sites. On the basis of these investigations, we found 16 periods of the highest fire activity from 1668 to 203. The mean time between the fires varies from 9 to 22 years, depending on forest type and human activity, whereas in the 18th century, the mean time interval between 2 fires was about 90 years. It is only 11 years in the 20th century. The occurrence of forest fires depended strongly on the precipitation during May and June. Most important cycles of dynamics of forest fires are one with a duration of 60 years and superimposed a cycle of 3 to 4 years. Thank you for your attention.
Thank you, Victor, for interesting presentation. Clearly, we'll have questions at the time when we'll have a poster session. Well, we continue with our program, and let me just check this quickly up where we are. Yeah. Yes, that's right. We have Guy Pinto, who is a PhD student at the Swedish Agricultural University. I feel like sound a bit strange. Yeah, anyway, he will be presenting results of ongoing study, and some of the results are quite preliminary, though we believe they're clearly worth discussing. So, Guy, the floor is yours.
Things in Russian here. Don't you need that? Good afternoon, everybody. My name is Guilherme Pinto. I'm a PhD student from Igor Drobyshev in Alnarp in Sweden. It's a very short presentation. I might try to answer some details afterwards if there's time for it. I'm presenting, as Igor said, an ongoing study on the patterns of modern fire activity in Sweden, looking mostly at the role of landscape and human factors on fire. Briefly about Sweden. Sweden is a quite large country in the northern hemisphere, not that far from here in comparison to other places. It has around 57% of the country. It's covered by forests, with 23 million hectares all around its extensions, from north to south, to the south. Per year, we have an average between 3,000 and 4,000 fires occurring, burning around 2,000 hectares. In comparison, as we saw with Russia or Canada, it's nothing. It's just you do this for barbecue, so it's all right. But for Sweden, it's relatively quite large. For fires in Sweden, we are using a data set from 1996 to 2012. Here, I just plotted for you to have an idea that in this period, in 16 years, you find fires pretty much everywhere on the landscape, including the alpine areas all the way there. And those are just the fires above 1 hectare. If we count in the same period larger fires over 1,000 hectares, we just have this 4 points here. Again, that's not much, and but considering the trend in this time, we have an increasing trend here of more fires occurring, and with a smaller area. So apparently, the area is decreasing while the occurrence is increasing. Though here, just go into 2012, and I'm pretty sure if we added up 2 fire events that was Fullman, yeah, was saying if we put here 2018 event, the trend shifts a little bit for increasing again because it's a shorter period. But as Igor on another study did in 2012, on the long term, the trend is really for the size of fires of going down and not up. Though still some larger events happens, like this one here is pictures from the 2014, that one single event burned 14,000 hectares, very unusual for Sweden. So you see quite a large area was burned. Though for those fires, we understand that climate is one of the biggest driver, of course, for fires for happening, long droughts and so on. But what we want to try to understand is that in Sweden, they are extremely effective in suppressing fires. That's why they happen in such a smaller scale. But then they still occur, and as we saw a lot, and so on. So our main idea was to look for associations between fire and landscape properties. In this case, we're looking for fire occurrence and fire sizes, 2 aspects of fires, and how they can correlate with the landscape. How can they interact with the landscape? So we hypothesized that there's a positive association between fire occurrence and landscape properties, though there's a negative correlation between the fire size and some landscape properties. For the methods, we collected data from several different sources, from the Swedish Civil Contingencies Agency, where we got our fire data, National Forestry Inventory to see how the forest looks like in the landscapes surrounding it, European Environmental Agency for land cover, and several other data from the Statistics Sweden about population and roads densities. The variables that we worked with were the vegetation zones, where each fire was, where each fire had happened. We have 7 in Sweden. Sorry, it's a bit small and bad to read. It's Nimero zone, Boreal Nimero zone, going more up, Southern Boreal zone, Middle Boreal zone, Northern Boreal zone, and up here, Alpine zone. This is a map for the road density in Sweden. Also, it follows a more gradient from north to south, where the south you have more roads around. Population as well was also another variable that we added. You see some bigger urban centers like Malmö, Göteborg, and Stockholm down here, and again going north you have a little bit less. Fire breaks, considering fire breaks in our, the amount of kilometers per square kilometer of, sorry, just a map for fire breaks, but fire breaks we added was water and or urban areas surrounding the fires. Forest dominance, we looked at spruce, pine, and other types of forests surrounding each fires, and we added 3 more. We added tree age, the Canadian Fire Weather Index, and the Initial Spread Index. Those 2 weather indexes just for fire size. I will explain a little bit why. The resolution for those data, everything 100 by 100 meters pixels, so several raster files, is quite heavy. And for the fire occurrence, we looked around each fire point. We collected 100 meter radius, so around 3.24 hectares, around each point of where each fire occurred. And for fire size, we looked around 1,000 meters surrounding its area to have a good idea about the landscape where the fires occurred. The point was that I was going for the initial spread index and the... Oh, sorry, it comes in a minute. So we collected all those variables, the data for those variables for the fires, and we used computer models to assess the influence of those variables, either on fire occurrence and on fire properties in the two different models. We selected from several models the best model with the lowest Watanabe-Akaike information criteria. A problem where we stopped it was when we bumped into spatial autocorrelation. As we saw, for example, road density, we have heavily, way more roads in the south than in the north, and that was a problem that we need to take care of. Otherwise, the bias for where the fire occurred would be a bit too heavy. Our regression models, where we treated as well the spatial correlation, we used the INLA SPDE models, so integrated nested Laplace approximation with stochastic partial differential equation. It's a very long name for it. But, to treat the fire occurrence, we used binomial models, including actual fires, so the fires that really happened between 1996 and 2012. And we randomized points around the landscape where we collected the same type of variables to compare where fires happened and where fires didn't, to see how the landscape or those variables affected actually the occurrence or not of fires. For the fire properties, we used area as the dependent variable with a logarithmic function as well for the discrepancies between the high amount of small fires to the other ones that's somewhat larger. The preliminary results so far for fire occurrence are, again it's a little bit too small, I'm sorry for that. The best model chosen had the 6 variables, so vegetation zones, fire breaks, again water in urban areas, population density, roads, trees age, and forest dominance. We have here 0 for 1, so 0 didn't happen to happen. So we have here, oh, I'm sorry. It's not working. Well, we have here that those 3 vegetation zones, they are more prone to happen of fires. In this sense, they would be the boreal nemoral zone, southern nemoral zone, and middle boreal zone. So that they are no, sorry, it's this boreal nemoral, and south nemoral zone. So they are more the 3 southernmost zones in Sweden. For occurrence, occurrence should happen according to our models more south. For the fire breaks, we found that where more water and urban areas are surrounding the areas, there are a higher chance of happening. We see this as 2 possibilities. One, for around urban areas, of course, you have more people going for barbecues, going out to the forests. The second one, for more water, it's because close to water bodies, we have small inlets, small peninsulas, and small islands where attract lightning. So we have, in this sense, closer to the water, a higher occurrence of lightning as well, so it's starting fires close to the water. Again, population density, of course, we have more people, you have more chances of fires, more people going out, doing barbecues, smoking cigarettes. As the roads densities as well increases, the amount of roads surrounding it, so you have also more fires, you have more traffic. Trees age, there's a decline in it. We understand this as, from the point of view of Swedes, normally when you speak to them, they don't like old forests. Old forests are too close, too complicated to go through. So they like younger forests just to walk through it. It's nicer, it's simpler. And that's why we see, as well as the forest dominance, we see deciduous and other types of forests as with a higher chance of fires happening at fires starting, just as an occurrence. Partially from our models, we are trying to as well to predict where actual fires. This would be a heat map from where fires occurred. We still need to validate those models, but if things go alright, if I remember well, around this area where we had a lot of fires this year, then we need to see. Here's the relative risk. It's a way of smoothing down those areas here. And for fire properties, we had those variables. Again, sorry for being so small. And here we have actually the place where, so we have vegetation zones, fire breaks, population, roads, trees age, forest dominance, so the same 6, plus initial spread index and fire weather index. Though different here, we have for vegetation zones, the vegetation zones with the highest chance of large fires is actually the middle boreal one, a little bit more up north. Again, where the large fires happened in 2014 and again 2018. As the fire breaks decrease, we also have a chance of larger fires. Of course, you have less people, you have more forested areas as well. Population density and road density, as they diminishes as well, you have a chance of larger fires. So we see as it's more complicated to people to report the fire and also to get to the fire to put them down. Tree ages increase the chances of larger fires as the older they get, possibly for fuel accumulation as well. Here it's very small. I prepared a thing that we could zoom it, but it's not working. So here pine, it's a little bit up. It's a tiny difference, but pine is more prone for larger fires. And of course, as we said before, initial spread index and fire weather index are the most drivers for large fires. Here just to point out again with the vegetation zones, so we have those mapped with the 4 largest fires that I had in the beginning, and here with all fires. So we see again that from this part down we have a larger occurrence of them, and here we have the larger fires. So again, corresponding to the middle one where large fires tend to happen, and the 3 southernmost ones where fire occurred more often, though not necessarily large. Again, as I said, it's a very short presentation. Thank you. Yeah. Those are the maps with all the names of the vegetation zones that they were supposed to go back and forth, but didn't work out. I'm sorry. Yeah.
Thank you, Guy. Well, I'm quite certain there will be some questions on that. A truly thought-provoking presentation. I do believe so.
So too short, too much in a rush, but yeah.
Yeah, I was wondering. So for the size of the fires, area of fires, is the build-up index, because you use the initial spread index, you use the fire weather index. So is the build-up index also not an important one, because you take the initial spread index, but why not the build-up index?
The point for this study was not necessarily to add climate data to it. We just add a few ones to try to see how the models would react with the input of some data. We did the same. I run the same models without climate data, and they're pretty much the same. I just put it to see how strong the lines actually for to point out how climate also as the most important drive is. Yeah, I just pick it to use it once.
Yes, but to follow with that question, when you do have on the model the ESI, ISI, and the FWI, as the FWI depends on ISI and BOI, you have a correlation of this variable inside your model. I would suspect that if you would use the ISI and the BOI, they would be less correlated, and with both, we would show up with the same trend, and they would provide you an idea of the total FWI that would act if you would include it. But I think BUI would be better than FWI in that sense, because the largest fire here, if you take the ISI, it's really like a kind of testing the propagation, the speed of the propagation, and the WI would be the amount of available fuel to allow that spread over a very large area. So I would suspect you would at least find the same good result as you do have, but with less correlated variables inside. And I think this would be better.
Okay, yeah, that's good to thank you.
Sorry. To clarify, did you have a variable, the size of stand or size of forest compartment?
No, not really. The ones that we use actually for forest dominance, again, sorry, we're just in a rush. It's the amount of cubic meters of wood in a pixel.
Because when we are trying to figure why there is a difference between Finland and Sweden, it's partly because, especially in the areas that you showed in the central and northern Sweden, because of the forest ownership, the compartments are much larger. So they and combined to this not as dense forest road network, they have time to develop into major fires when they are after that's hard to extinguish. So I think it's rather a question of this than the vegetation zone that you have this larger scale forest, larger forested areas, and that explains the large fires, in my opinion.
Yeah,
partially.
For the forest dominance there, I didn't went into details, but what we did there, we took the amount of cubic meters of wood divided either in spruce, pine, and other types of wood. Normally deciduous is the majority, and we verified which one of them has the majority of percentage in those areas surrounding each fire. It would be possible maybe even to look specific in each type of them, but we want to see how was the effect of the majority, how the broader picture of the situation around each fire was.
But you didn't have the area of one single stand, how large it is in average, because I think this continuity of forest is a quite good explainer, probably.
Yeah, no, we didn't look at it. We went a bit more focal.
Okay. More comments, questions, concerns? Well, I have one actually. There's one result which I'd like to articulate more in your presentation, but that's that we have country which is largely in the boreal zone, and the distribution of fires pops up in the way that most of the fires happen in the places where we don't have large fires. So we'll have most of the fires happening in southern Sweden, but larger fires are actually happening in mid or north Sweden. So it really brings up the question about the consistency of this pattern in the past. Is it something driven by vegetation, which is clearly different? We'll have a gradient from Nemeral towards northern boreal, well, not so much alpine really, we have to talk about it, but northern boreal vegetation. But we also have quite a gradient in terms of climate variability. We'll have more temperature, we may have more wetness also in the south, right, and somewhat cooler and dry weather up north. So I think this point clearly outside the scope of the current study worth maybe articulating a bit more and sort of bringing it up in the discussion, because this is something which is probably quite common not only for Sweden but also for other parts of the boreal zone, right? Again, it's a function of fire suppression, it's a function of vegetation, it's a function of climate variability. And since we model things forward into the future, if we want to increase realism in this modeling, we clearly have to address that if we believe it's consistent pattern or not. It seems like it is, right? Any comment on that?
No.
Thank you.
Thank you.
Okay. Yeah, Tadeusz, I see you're getting ready to say something really. Yeah? Okay, sure. Okay. Okay. Good. Then we thank you, Guy, again for the instructive presentation. Yes, and now I have a pleasure to welcome Shema, who will tell us about the history of forest fires, guess where? In Russia, but in a very long time perspective.
Where is the little pointer? Do you have?
As I understand you need
Okay.
this.
Thank you. Thank you. Okay. So hello everybody. I'm really happy to be here to present you the first results of my PhD, which are focused on the Holocene fire history in Komi Republic in the Ural regions of Russia. So I made this work with a lot of people who are here today. We already talked about that this morning, but I will make a quick resume of that. So why the boreal forest is important? It represents 30% of the world's forested areas, and this is the most important reservoir of terrestrial carbon, which is stored in soil and peat sediments. And fire is the main disturbance of this forest. And knowing that climate is changing, we can wonder how it is going to affect the fire activity and how it is going to affect the boreal forest. So, as I said, these results are focused on the Komi Republic, which is this region here, and my study sites, which are here, are represented here. So this is in the northern Ural region, in the western slope of the Ural. And the study sites are on taiga forest, which is mainly composed of Pinus sylvestris, and species of Betula. This is a region which is really sparsely inhabited, and today there is about 2 inhabitants for 1 kilometer square. And the fire events from today are mainly human-induced. So the question that I had when I began to study this region about the fire activity was to know in what part the climate, the vegetation, and the human activity was involved and drives the fire activity. So I could wonder, for example, if when in the Holocene the climate was warmer, was there higher activity or not? What was the role of the vegetation, and was there direct link between one of these drivers, or was there complex interaction between them? So to try to answer this question and to, in the first time, have the fire activity, I made a multi-proxy analysis. So the first part of this analysis was the sedimentary charcoal analysis. This was done on 2 of the 3 sites here, and we called each site twice. So for each site, I have actually 2 cores. Once I had this cores, I
cutted it each 0.5 centimeter, sorry, and I counted and measured the charcoal particles. So after that I made an H model, and I used the measurement of the particles with the software char analysis to interpolate the char data into two populations, charcoal background and charcoal peak. And the charcoal peaks allowed me to have the fire events here indicated with the red crosses, and to have the dates of the fire events. And with that, I could calculate the FRI, so the fire return interval. And the fire return interval is the number of years between two fire events. So the more the fire interval is big, the less there is a fire activity. So the second kind of analysis I have done was the tree rings analysis, which was done on the tree sites. So after dyeing and sanding the cross-sections, I dated the fire scars which were on the cross-section of the dead trees that we have sampled on the field. And I made a cross-dating between the sites with topswing. And I assumed to have fire events when I had at least 3 trees which show the same fire scar for the same dates. So this is the main results I had for the fire story with the sedimentary analysis. So this is a pooled FRI reconstruction of the 4 cores with a kernel density function. And what we can see is that in the beginning of the Holocene, the FRI was pretty high. It was around 4,000 years. But there is a gradually decrease of the FRI, and today it's more about 50 years. So the fire activity has consistently increased during the Holocene. These are the results with the tree rings analysis, which show the fire activity in a more short time. I could reconstruct the fire activity until, sorry, this is really little, but this is until 1600 years AD. And this is the diagram of the fire scars for each site, and here for all the 3 sites. And we can see that there is fire events which are shared for the 3 sites, and there is fire events which happened just at one site. But when we look at the fire return interval, which is comprised between 36 years and 75 years, it's well adequated to the result that I had with the sedimentary reconstruction. So once I had this fire activity, which is here, I tried to compare it with the fire activity that I could find in the literature. So that's what I've done here at the scale of all the northern extratropics, where we can see also an increase in the fire activity, because here it's plus, here it's minus. And at the middle of the Holocene, we can see that the results are also consistent with the one made in Phenoscandia. So what we know in terms of climate in the region that are neighboring the study site, is that because of the decrease of the insolation, there was a decrease in temperature. In the first half of the Holocene, there was a warmer but moister climate, and this in the second half of the Holocene, there was a cooler but drier climate. So I can guess that in terms of climate, the moisture was more important than the temperature in driving the fire activity. In terms of human activity, so as I said, the Communist Republic and more largely the Ura region was really scarcely inhabited during the Holocene, but there is a huge increase during the last 5 centuries, and the very sharp decrease in FRI, so increase in fire activity, than we can saw in the figure, could be related to the increase in human activity in this region. Well, that's new results that I have on my data, because the fire activity is the first chapter of my PhD, and then to know better about the interaction between climate, human, and vegetation, I made the pollen analysis of the same cores that I have studied for the charcoal. And I have done this analysis for 2 of the 4 cores through the traditional chemicals and physical treatments. And for each core, I counted a minimum of 300 pollen. For each sample, I counted a minimum of 300 pollens. And that are the very first results of the very first results of the analysis that I did not finish to understand. So if you have suggestions, it will be welcoming. So what we can see here, first, this is the fire activity, which is not a pool. This is the fire activity of the core YAC2. And this is the pollen analysis that I have, the terrestrial pollen analysis that I have for this core. So here we can see that there is, during all the Holocene, it was a forested area. And this is the curves for Betula. This is the curve for Pinus aploxylon type, so for Pinus sylvestris. And this is the curves for Picea. And here we have the results for the YAC3 site, which does not cover all of the Holocene, but just the half. And we have a more thinner resolution, but the results are not really in well adequacy between them. So that's why it's still I try to understand what was going on, and keeping in mind what was the fire activity of the region. So to conclude on the result about the fire, at this point I cannot have with really sure idea what was the main driver between climate, vegetation, and human activity, but I can guess that during the main part of the Holocene, where the human population was really low, the climate was really more involved controlling the fire activity, and especially the moisture of the climate. And in the last 5 centuries, the fire activity has been more important, controlling the fire activity. So there is still ongoing work about that, which are the analysis of the pollen results that I have showed you, the climate modelization through this pollen, and a last one, proxy, which is GDGT, which is glyceryl dialkyl glyceryl tetraether, which is a complicated chemical name to represent the lipids membrane of bacterial components which are ubiquitous in the soil and in the pit, and which are very well correlated with the mean temperature. So that's it, and thank you for listening. If you have some questions.
Yes, please, questions.
If there is no question, it's okay.
You are dealing with samples from Komi Republic.
Yes.
Don't you have also trees like Siberian larch and Siberian fir there
No,
as well?
just pinus.
In Komi Republic?
Yes. We sampled just dead trees, pinus dead trees.
Sorry?
Just the pinus dead trees.
Yeah, I mean in the forest, as natural trees, you have also Siberian larch growing in the Komi Republic, don't you?
Oh yeah, but the majority of the species is Pinus sylvestris and.
Yes, I was just wondering in your paleo records if you're finding any larynx remains, like larynx pollen or.
Well, I don't have found
yes.
some of it, so maybe it's a question of taphonomic processes,
yeah.
but I don't have found large pollen.
I have a short question. You discussed fire, and clearly the territory was pretty much uninhabited by modern standards, so reasonable assumption that the fire-driven system we have been studying here. But you also mentioned that there are methods which are currently in use to look at the imprint of human presence in the landscape, this bacteria which lives on the poo of the cow and stuff like that, or for example the Gramineae, right, which would be another proxy for human presence.
Yes.
Did you try to look at this and see if there are any thresholds or any dates you can establish?
I didn't really. Can you repeat?
Okay.
I didn't really.
I wonder if you looked at any proxy of human presence which you may have in the pollen record.
Yes.
If you did, can you see any thresholds in the presence of people in this area?
No, well, that I put on the screen was all the terrestrial pollen that I have found in my course. So I have also the aquatics one that I didn't show there, but I have not traces of, for example, agricultural species which were there. I didn't find them in my course. Yes. Does not mean that there was not there, but me, I didn't find there.
Okay. But basically, did I get it right? It's basically proof the landscape is pretty much in like natural state. If you look at the very long-term perspective, right? There have been no major colonization waves that we can really disregard this factor.
Yes.
The human presence. Right?
Yes. Yes.
Mm-hmm.
Mm.
Mm-hmm.
Well, but the Komi Republic is still really sparsely inhabited.
Yes.
Even if there is a huge increase compared to the other part of the Holocene, this is still poorly, sparsely inhabited.
Specifically that area which you studied.
Yeah.
That's true. Because quite often people argue that, well, for example, fire activity, right? We often study fire activity close to the roads,
Mm-hmm.
right? We need access to the spots and preferably easy access, right? So these roads there clearly were migration paths for the ignitions, right? Historical ignitions, mostly human-rated ignitions, though you can debate how much human ignitions were contributing to the total amount of fire, but yet, right? The argument which people often put forward is you have to go to the spot where we don't have roads, we have nothing, like till today. And in this case, I think we'll have this. This is the case. That's what it is.
Not easy to reach. Not easy to reach.
Yes, not easy to reach. Yes. the true sense of this word. Yes. Okay. No. Okay. Good. So, thank you very much indeed. Well, I think it's time for Gwenel. Gwenel works with paleo, fire too, but this time we move to the west, right? Going against the jet stream. So this would be a story of paleo fire activity, but in the northern boreal forest. Yes.
So, hi everybody, I'm Gwenel Magne. I'm a PhD student with Adam Ali in Montpellier University and Emmanuel Gandouin in Aix-Marseille University. And I work in relation between paleo fire and the climate in the past. I think I know the importance of boreal forest in the world, and my work is I'm interested by the boreal forest in Finno-Scandia, principally in Republic of Karelia and in Lapland in the north of Finland. So we know the relation between climate and boreal forest and the fire dynamics and the forest, but the link between the climate and the fire are not completely understood. And with the Boreal project, I study this in the past for understand this and in the future with the climate changes. In the first past, I study the fire history with the charcoal. There are two methods for reconstruct the fire history: the dendrochronology with the fire scar and the charcoal. These ones are very precise for dating fire, but they are limited in the time. And charcoal are for the long time, the complete Holocene, but not also precise than dendrochronology. And there is two systems of fire: crawling fire, more in Canada and North America, and surface fire, more in Eurasia. This one produces many charcoal, so it's more easy to detect this fire event. But this one, the fire burn only the under of the forest, so there are not many charcoal. It's it's very difficult to detect. So the question here is: it's possible to detect the surface fire with the charcoal method. For this, we study two lakes in Karelia, not far from the Kalevala National Park. And we study the variability of charcoal concentration, so 1 centimeter and 3 centimeter of sediment. The water content, because there are more water in, so less sediment and less charcoal in the top of the surface sediment, and in the back there are not water, so more sediment. And we compare this with conical data for reference. This is the two lakes, Lower Lake and Jinko Lake, distant by 200 meters. And the 73, it's all Pinus sylvestris sampled. They are dead tree and living tree. and the work field is in 2050, so before my PhD. After the dendrochronological analysis, we have 12 fire dates you have here, and the black cross are the fire event. There are 3 important fires. We see this with the establishment of a new cohort 3 after the fire. And we count also this fire as an important event because there are a lot of scar fire on the tree for this fire, for this event. Here there is the comparison between the data of dendrochronology and the data of charcoal. So you have the fire date and in gray the important fire. And here we have the Jinko Lake and Lower Lake, and the data, the result with after charcoal analysis and interpolation for 1 centimeters and 3 centimeters, and with the number of particles of charcoal, the total area of particle in one subsample, sorry, and the estimated volume of particle with the Wang equation. So we compare all of this. It seems we can detect surface fire, but it's a little difficult because, as you can see, fire, maybe this one and this one are detected only on Lower and this one only on Jico. The fire are not detected. This one, for example, is detected with a lot of sediment, but not with a small volume. But this one, yes, and no with a lot of volume. So there are big variability in the sampling for the charcoal particle because they are less charcoal particle. And so it's possible to detect this fire, but it's important to have a replica and to sampling different lake for a good reconstruction. For the climate, for the paleoclimate, we're interested for this site in Lapland, and I use a paleological proxy, the chironomid. So the chironomid are insects, and the larva is aquatic. She have a head capsule very chitinous, and this capsule is fall in the sediment, and we can study this and determine the species. There are 10,000 species in the world, and each species has the temperature specificities, so it's possible to extrapolate and reconstruct the paleoclimate with this species. And it's not a proxy linked to the vegetation like pollen, for example, so it's better for compare this to the fire history. I present you here the result of a preliminary study in the lab 19, sorry. The methodology is a classical treatment like Brooks and Al say. So we treat the sediment for cleaning the head capsule and determine it in the microscope. And so there are the 3 lakes in Lapland. For each lake, we study, it's ongoing actually, the charcoal particles, the dendrochronological data, palynology with the help of Norman Strivins is in Lapland University, and chironomid for 2 lakes, Lake 4 and Lake 19. This is the preliminary study for the Lake 19. For this one, there are 73 subsamples, so it's 6,000 head capsule, and we use the 24 major taxa for this analysis. And we test this with the correspondence analysis, so we have the result here. The axis one is a very good temperature signal, with on this side the warm term taxa with Palidicornis nubifera, for example, or Chironomus plumosus, and this cold stenotherm taxa with Tienemaniema, for example. The axis 2 is more complicated, it's probably a macrophyte cover gradient, but this depends to the level of water, the vegetation, so it's not a signal as good as the temperature signal. Here we have the diagram abundance of the principal taxa of chironomid, with this the warm and here the cold taxa. And we have in the beginning of the history of the lake in 7,000 years, it's a lake very lithotrophic, with not a lot of diversity and species very warm. And in the different in the time, the different species, and in these periods the more cold species. Here the signal with the score of the axis 1 and the axis 2 of the correspondence analysis. We compare this signal with the bibliography, so whose results are validated by the biblio, because the warm period, for example, corresponds to the optimum Holocene climatic, and our cold optimum climatic here is in the little ice age period, little ice age, sorry. So we have a strong signal temperature with preliminary studies, and we record Holocene no event. In the future, we study this with high resolution. I work on this actually, with 2 chironomid sequence and the pollen. Chironomid is more for the temperature signal, and pollen we won't use for the rainfall signal. And we use after transfer function with the help of Tommy Lyoto for change the chironomid signal in real temperature construction. And after, with this, we can compare the climate history of this light plant side with the fire history with charcoal and dander. So here from a moment and
Good night. Well, time for questions.
Not question.
Okay, I have a question. If we come back to the very beginning when you was talking about the possibility to recover the same events from the Palea record as the ones you see in the Dendra record, that was the first part of your presentation.
The Dendra?
Part number 1 of your presentation.
Yes.
I don't recall the slide number. So I see that, yeah, that's right.
This slide?
Yeah, yes. So I see there's like naturally not a perfect fit between 2 types of proxy. And I think it will be very interesting to just discuss why this is like that. We have issue with just first the deposition, right? Like
yes.
you have certain amount of charcoal which not deposited, right, on this for some reason, or not deposited in the amount which you would identify it as a peak, right? And probably you also have, and that's exactly my question, you probably also have fires which were happening outside the area which was sampled, right? So you have you may have certain fires which were missing from the nearest spot, like this places between two lakes, which you sampled dendrochronologically. But you may have fires which happened in the vicinity outside this area which you sampled dendrochronologically, right? So you may have both underestimation and overestimation of fires, right? The final result in the paleo record, right? What do you think it will end up with? Is it more overestimation or underestimation? Or it's purely a function of threshold, which you said?
I think it's more in English. The signal with charcoal is more we have not all the events because they are really the charcoal particles are really rare. For example, the maximum of particles in one subsample is 7. So there are no bruit de fond, comment on dit? No background of charcoal, and they had little peak for the event, but with this, the peak are a fire event, but when we have 2 charcoal, sorry, it's difficult to know if this are a fire event or no.
Okay. If, say, we want to just imagine a situation, we have no constraints in the paleo reconstruction, no financial constraints, no time constraints, limited amount of students who can do the stuff, right? Where we should put our effort at first place to approach the precision of dendro reconstruction.
Si on n'avait pas soit beaucoup d'argent, pas de limite, comment on ferait pour justement augmenter la précision?
Yes, the better method is sampled a lot of lake with different sequences with 3 replicates of each level, and we can detect all the fire. But
okay, but can you identify the major source of uncertainty in this? Like, if you would just select one way to improve the resolution, right? Would you sample more lakes? Would you sample the same amount of lakes but more frequently and create a better age model? Would you do something else? What would be like the main source of this confusion which we have here?
In first time, it's already it's important to sample different lake because the charcoal deposit depend of exterior condition, for example, the wind, and we can see with the 2 lakes in this example are very not far one for the other, but we detect fire on the one and not fire on the second lake, so it's maybe the wind. So in first time different lake. And for one lake, a big sediment volume are more interesting for a good evaluation of the charcoal number of particles.
Okay,
I think.
Adam, please comment on that.
That we can see in this table, I think that we need to perform because Gwenel use when you have charcoal, we have some numerical treatment that the main goal is to remove the background, because when you have a fire, you have the peak of the fire, but also during a long period we have also charcoal that coming from this fire during a long period that continue to put charcoal in the sediment, it's a very big issue, because sometimes it's not easy to be sure that the peak corresponds to the fire, because we have this kind of background that continue to put charcoal in the sediment. But we need to keep in mind that it's a fire event, and on one peak we can have several events, because that's why we cannot say it's a fire episode, but mostly a fire events, because in one peak we can record several fires. So it's quite. I think that it could be useless to try to reach the accuracy of dendro, because for this point, in one peak, we can have several fires that could be recorded in this peak, and it depends also to the precision of your age deep models. It also depends to the sedimentation of your lachrystine deposits. If we can check and if you can have some valve sediments that it's something very annually deposits, that could be good, but it's not so easy to find this kind of deposit in boreal ecosystems. So for me, even if we deal with a fire return interval to say, okay, we have now a frequency of fire, or the fire return interval between two consecutive fire, I think that it's a way to illustrate the fire activity, but we cannot take it as a precision of the frequency of fire study area. We just use it as a tool to illustrate your fire activity, but normally we need to use a lot of sites, a lot of lachrystine deposit, and to make a kind of synthesis, and to be sure that, okay, in the past you have high fire activity during 8,000 years ago and between 5,000 years ago, and after you have a decrease of fire activity. But to say, okay, exactly, the fire frequency is 100 years or 200 years, and after you have a decrease up to, I don't know, 50 years. So I think that could be dangerous, because in one peak we can have solar fire that could be recorded in one peak. So that's, for me, it's a big issue. But in the case of Grenelle, we need to see if surface fire could be recorded in sediment, because the big issue is the quantity of charcoal produced by fires during this kind of fire activity. When we deal with crown fire, it's quite easy, because crown fire just burn all the landscape, and you have a lot of charcoal that can be put and can be recorded in the sediment. In the case of surface fire, and that is say, in the sample we just have 5 particles, and when we deal with charcoal crown fire in Canada, you can have up to 200 particles in the 1 centimeter cube. So the main question is, in this case, how we can reconstruct surface fire and using lachrystine deposit. I think that in this case, we just see that you have identified 12 fire with a dendrochronological setting, and it's very hard to find this fire, and in the context of high frequency that can be recorded in this area. So it's not easy.
Yeah, thank you, Adam. I think there's a comment on that.
Well, if we would not have a problem of money, for instance, I would say that as I know that there are some prescribed fire that are used for management, to manage territories, what we could suggest is that we could, and to see what is the amount of charcoal that surface fire can produce. So prescribed fires are usually surface fire as well. So if they are planned or planified or scheduled, let's say, over the spring or summer, I think we could put some charcoal trap or pollen trap inside the lakes, near the planification or planned prescribed burn, and the idea would be to see what is the amount of charcoal that can reach the lake on the fire on the same year or the same season, but also maybe later on, because with surface fire we can imagine that the transportation, the wind blowing and transport is very less efficient for charcoal, so maybe it's more kind of runoff and slowly maybe charcoals are coming, but 1 or 2 or 3 years later, because they were not a lot, and so they finally reached the lake. So I think we should monitor that, provide monitoring on this, just to have an idea about if it's valuable. Well, I mean, if it's worth to work with that, because the less intensity fires have, could be some charcoals, but not a lot, and if it's too intense, we could only have ash and no more charcoal as well. So it's.
But I think right in this aspect, you are quite lucky, because it was a recent study, and I believe Adam will just want to say about that.
It's a very good idea. We do it with France Oris in the Crown Fire in Canada, because we put some trap, not here, but when we try to do it, we see that the fire, when it occurs around the lake, just burns a part of the lake and can let some part not burned by the fire. And when we put this kind of trap in the sediment and also in the soil around the lake, we have seen that the main charcoal not coming from the fire that occurred during this date, but two years after, sometime. And after we have a big fire that occurred very far from the lake, and this fire put more charcoal than the fire that occurred very close to the lake. But particularly is bigger when we deal with the local fire compared to the fire that occurred very far from the sites. And also, initially, when I deal with charcoal and in the lake sediment, some people just told me, oh, you know, when we deal with the peak and the amplitude of the peak, that could be a proxy to say that the fire occurred very close to the lake. Is not true, because sometimes fire that very big but occur very far from the site could induce a peak higher than a fire that occur very locally. So I think that yes, this kind of design must be important for us, and we need to push in this direction. That's why I put this kind of design to make some kind of correlation between dendro and charcoal, and we get trouble because we just say, okay, it's not good, because now we just say we have 12 fire, we just detect 2 and 3. What's happening when we deal with the long sequences? What can it do? What can I say with this kind of recording? But
I think that brings quite an interesting point in that. I fully share your perspective, even from the endocrinological point of view, that all fires are not equal, as racist it may sound, right? We have fires which really impact the landscape, and fires dated whatever method you use, which are relatively marginal, highly unimportant in terms of ecological, economical, societal impacts, right? These small fires which you always find, and probably 80% of the fires which are on this list are also of any measurable impact. They happen, but they really have nothing to contribute at a larger scale. So my point is that, and these fires you have in your record, in these fires we have in Denver record, right? Yeah. So when we calibrate this, we calibrate two things. We try to calibrate a mixture of two types. Fires which are really relevant, which really want to understand, which people model, right, and people really discuss. And those which simply, to a certain degree, a noise, right? They are there, they're a natural process, but they are a noise, right? So would it be a pragmatic yet very way more manageable approach just to focus calibration exclusively on the large events. So in this case, we need somewhat better replication within your landscape, and then we need dendro record, which brings up this large fire events. And then we simply disregard those which are just...
That's why we try to do it with 2 lakes and try to take fire scare in the different tree around the lake. But I think that we need also to discuss about that we do in this area to take the main fire in the landscape in order to see if this fire reach also the lake shore of these 2 lakes. But that we need also to explore another proxy. You know, we have a PhD student, Carol Bastianelli, that also use a new proxy. It's not a new proxy, but a proxy not usually used in paleoecology is a biochemical signal in sediment, and we try to see if this biochemical signal could be correlated with the signal of the fire using charcoal, and we have good results also. So even if it's not easy to use this charcoal in lake sediment in order to reconstruct fire activity in the past, you have a lot of good signals, independent signals also, vegetation, biochemical signal, and chironomid that help us to say that using charcoal in order to reconstruct past fire activity is a good proxy to do it, because for the long period we don't have another proxy to be used in order to have this kind of information about fire activity in the past. Not yet, but now.
Not yet. Okay, well, I think we thank you, Cornel, for letting us come up with this hopefully very stimulating discussion. Well, thank you very much indeed.
Thanks.
And with that, I think we round up our day. Just want to make a couple of announcements. We're going to have dinner at 7 o'clock at the place we all stay, apart from Berg, right? Yeah, right. That's right. You follow us. That's right. 7 o'clock, and I do promise there will be higher diversity of food than the one we experienced during the lunchtime. I do apologize for that. And then, yes, we'll do our best. That's right, as always. And tomorrow we start at 8 o'clock, right? So if you are 7:50, let's put it this way. So if you are in a position to enjoy breakfast at its fullest, I do suggest you actually start then earlier than today, right? So at 8 o'clock we actually depart, right? We want to have, we will stay mostly outside, and we'll also experience a sampling. For some of you it's more or less like not a big deal, but I hope it will be interesting still for some, and very interesting for some others, right? And then we expect it to be back around between 4 and 5 o'clock, right? So if you have your proper boots and somewhat more tough clothes, bring them. And we will have lunch at the national park, right? Yes, and we will have a coffee break somewhere in the forest too. So don't consume everything you will see in the morning at the. Yeah, but with that, I think if there are no comments or concerns, then I'll just thank you.
In Frigate, 2 times happy, because today at 7 dinner, and tomorrow at 8 o'clock in the morning depart. And as you can see, at 5 o'clock it's dark, and at 8 o'clock in the morning dark too. So we will come to Заповедник Kivaч when only in the beginning of the day, and we'll go out at the end of the day. But it will be a very short day. If you have questions, 7 o'clock, the most important event. Poster.
Yeah, that's right. Don't forget we'll have some posters, so please take a look and engage.
C'est pas un problème.
Ну, не. Но это вы про Wi-Fi, да?
Про Wi-Fi, и, значит, там эту камеру нельзя будет поставить?
Вот я думаю, что придется ее, наверное, да. Но надо будет транслировать. Микрофон возьмем от вашего коллеги, потому что у нас другого лучшего нету. Она вот звук не понимает.
Надо будет через скайп транслировать.
Не, я проверю, да, что скайп с ней работает, безусловно, конечно, да. Там удобно, что она крутится, можно там предустановки ставить, и если как бы скайп ее возьмет, я сейчас проверю, я думаю, возьмет. Хорошо, то есть звук у меня вроде как есть, слава богу, какой-то. Единственное, что очень короткий провод. Мне, ну вот у меня компьютер будет где-то там в углу вашего кабинета, я не знаю, совсем вот эти вот барахлы, вот полный
то есть ты хочешь компьютер?
А он без компьютера никак не работает вообще.